Hello everyone, I'm Yu Zhang. This study was accomplished jointly with Professor Sergei Golach at the University of Münster, which is located in Münster, Germany. Let's start. Mobile event-based social network platforms, such as Meetup, Plancast, Douban, and others, provide users with online-to-offline services, which are illustrated in the figure as follows. The event organizer publishes the relevant information about the event, such as temporal and spatial information, and attributes, for example, gatherings, sports activities, on the mobile EBSM platform. Then the platform will push the information to potential participants who might be interested to attend. The challenging problem in mobile EBSMs is how to efficiently recommend to users those events in which they are really interested. For the purpose of recommending relevant events to users, the existing recommendation strategies are useful in analyzing which type of events users are interested in. But they cannot accurately predict which particular events users will eventually choose to participate in, and they only consider the user's preference for events. Furthermore, the existing system do not take into account that event organizers usually seek to attract the individuals with high influence and reliability to their events. Due to such participants, the event can be held successfully and achieve the expected effects. In summary, the problem of the existing techniques is that they do not reflect the bilateral two-way nature of efficient event planning. First, events enroll more influential participants. Second, participants are arranged to events they are most interested in. In this paper, we improve recommendation process such that it will satisfy the needs of both the event organizers and the users. Firstly, we formalize typical scenarios of the recommendation process. We assume that an EBSM contains users and events. Formal definitions of the related concepts are provided in the following. Each user has an associated travel budget. A user's interest in an event is correlated by a utility score, and the interactive influence weight denotes user UI influence on the other user UX at event e.g. In this paper, we formalize the problem of recommending events to participants as a bilateral recommendation problem with two objectives. First, maximize the total utility score of the users to their arranged events. Second, achieve enrolling of maximally influential users to participate in the events. Well, the following constraints are satisfied. First, users' plans have no time conflicts. Second, users' travel costs satisfy their travel budgets. Third, events participation upper bounds are satisfied. We propose a method for computing the utility score of users to events using the behavioral sequence of a user within the user's travel budgets. As shown in this table, in order to allow for a convenient representation of the user's selection process, the behavior sequence is segmented. Take each attend operations as a split point, thus resulting in selection sessions from one split point to another. In this way, we obtain the behavior sequence for each user in different selection sessions. We name this approach a utility score estimation method in order to precisely estimate the utility score of users to events. We first empirically analyze the factors which affect user selection of events in the behavioral sequence of a user. As shown in this real-world behavior sequence, we sort each event according to the occurrence frequency from the highest to the lowest in a selection session, and then we obtain the percentage of E3 in the frequency ranking. Similarly, we sort each event in the chronological order in a session and obtain the percentage of E3 in the recency ranking. Figure shows the result of our empirical analysis using the real-world dataset. The frequency and recency ranks of the attended event distribution in our selection sessions. The y-coordinate represents the total number of the attended events in our selection sessions, and the x-coordinate represents the percentage of the attended events in the frequency ranking and the recency ranking respectively. For example, in Figure A, the first column shows that nearly 41 attended events are in the top 10% of the recency ranking. We observe that a large part of the attended events are both in the top 30% in the frequency rank distribution and the recency rank distribution. This confirms that real users tend to attend the event, which occurs more frequently in the behavioral sequence and which the user recently clicked on in a selection session. So our method USEM takes into account these two factors, frequency and recency. For example, if a user's behavioral sequence in a selection session is this, then the user is more likely to select E1 than E2. Our USEM method of calculating the utility score in this formula. Here is a small example of using this formula. Next, we consider the other objective, the influence of users. In order to precisely reproduce and study the complex individual interactions in social networks, we built a mathematical model of a social network. First, we start from a network with M0 nodes and add one new node at a time. Second, we assume that the probability that the new node I is connected to an existing node J is 1 minus p. Third, node I randomly selects node R to connect to with the connection probability p. In this way, a triangular linking network is generated. The statistical analysis shows that the clustering coefficient in real-life EBSNs is usually high, and it follows a power law distribution. There is the so-called skew-free network. The degree distribution follows at least asymptotically a power law distribution. And the most notable characteristic of a skew-free network is that the degree of our vertices generally greatly exceeds the average, where the degree of our vertex is the number of the edges incident to it. Real-world EBSNs are remarkably similar to skew-free networks, so we use skew-free networks as a suitable model for social networks in real life. We use the triangle linking network to adjust the clustering coefficient according to the value of the probability p. That is because the bigger the probability p of connecting two nodes, the bigger is the clustering coefficient. We simulate social networks using a skew-free network model with a variable clustering coefficient, and the degree distribution of the clustering coefficient that follows a power law distribution. Now, we estimate the interactive influence of users. We consider these three parameters which influence the interaction behavior of users. We illustrate our approach to modeling the interactive influence in a social network by using the recent COVID-19 pandemic scenario. Due to the safety concerns and statutory restrictions that prevent travels and gatherings, most of the users' friends are closely following the COVID-19 regulations, and not all of his friends are willing to take part in some shared event. If we assume that user UI interacts with a friend UX, the following conditions need to be satisfied. On the one hand, UX is interested in the event shared by UI. On the other hand, users whose preference ranks are higher than UX will not participate in the shared event, regardless of whether they are interested in the event shared by UI or not. In this way, we can calculate the probability of UX being selected as an interactive user. If the probability is 1, the UX is added into the set of interactive nodes. We name the set of interactive nodes a preference group. Then we define the ratio of mutual friends among users as interpersonal similarity. We express the frequency of information interaction among users using interaction strings. Next, we use the interpersonal similarity and interaction strings as the components of the interactive influence of a user. Thus, the interactive influence of UI on UX can be calculated. Here we show the pseudocode of our proposed recommendation strategy. The 3 important steps are here. We first find the most relevant events for each user according to the utility score computed using the USEM method. Then we analyze whether the capacity bounds of the events are satisfied. And we select the interactive users with the highest influence to replace the users with the smallest utility score in the current recommendation. We conduct a comprehensive experimental study on a real-world dataset. The vast majority of recorded user operations are click operations, where attempt operations only account for less than 1% of the recorded operations. Therefore, we pre-process the original worldwide meetup dataset by deleting information that has a low relevance for our experiments, such that the algorithm can work with useful data. We conduct a power law curve fitting process on the data of the skill-free network and a real-world meetup dataset of a mobile EBSAN, such that we can obtain the parameters which are used to simulate the social network. And we use the pre-processed dataset of Vancouver to evaluate the scalability and the effectiveness of our bilateral recommendation strategy. We conduct experiments to compare our USEM method with 3 intuitive methods: random selection, most popular event, collaborative filtering. We observe that our method can accurately predict the selection preferences of the users. In the next experiment, we look for the optional value of the weight parameters alpha, which is used to reasonably balance the influence of interpersonal similarity and the interaction strings on the interactive influence. We observe that precision is highest when alpha is equal to 0.6. Therefore, we set the weight parameter alpha is 0.6 in all future experiments. This figure compares the unilateral planning algorithm with our bilateral recommendation strategy. We can observe that our bilateral recommendation strategy achieves higher utility score than the unilateral planning algorithm. Overall, our bilateral recommendation strategy performs better than the unilateral planning algorithm in all 3 aspects: the satisfaction of the users, the satisfaction of the event organizers, and the total utility scores. This confirms the effectiveness of our proposed recommendation strategy. The only drawback of our approach is that it takes more time. However, since the absolute time spent by the bilateral strategy is not very high, it usually can be tolerated in real-world situations. In summary, We propose a novel approach to the recommendation problem within modern mobile event-based social networks. We provide a formal formulation and a mathematical model of the bilateral recommendation problem. Our extensive experiments over real-world datasets demonstrate the precision, effectiveness, and the scalability of our bilateral recommendation strategy. To the best of our knowledge, our work is the first to consider both the above two criteria together, such that events enroll more influential participants, and the participants are arranged with the events interesting for them personally. Our future work will attempt to improve the performance of the implementation. Okay, that is all my presentation. If you have any question, please feel free to ask me. Thanks for your attention.
Hello everyone, my name is Valeriu Stanciu, and today I'm going to present to you our paper, K-Anonymous Crowdflow Analytics. This paper is joint work of University of Twente, the Netherlands, with University Polytechnica of Bucharest, Romania. First of all, let's discuss a little bit about the context of our work. People have been interested in understanding pedestrian behavior for many years. Being able to discover movement patterns of crowds has proven to be highly useful in a wide range of domains, from urban planning or traffic optimization to even more critical fields such as public safety. There were many ways to do it, including technologies such as video cameras, mechanical counters, RFIDs, infrared, and so on. Anyhow, for many reasons, the most popular came to be a method which relies on sensing signals sent by our smartphones. Imagine that these devices that we all carry in our pockets transmit in the air from time to time Wi-Fi or Bluetooth signals. These signals can be then easily picked up by a sensing infrastructure which uses them for building crowd information. Nowadays, such systems are widely deployed. However, performing this process raises a couple of privacy concerns. Insights about the crowd are actually built on information about the individuals that take part in it. These individuals are identified by the MAC address contained in the signals sent by their mobile devices and captured by the sensing infrastructure. Having this unique association exposes individuals to a lot of threats, leaving the door open for unconsented tracking, profiling, surveillance, as well as more impactful scenarios generated by potential data leaks. As an attempted mitigation, pseudonymization was adopted on a large scale. So instead of storing the MAC address itself, they would store a unique pseudonym computed with it. However, the problem remains because essentially a pseudonym is still a unique identifier being attached to an individual. Recently, this has also become the subject of an increasing number of legal actions. We can even see crowd monitoring initiatives being halted for not complying with data protection regulations, such as, for example, the GDPR, which came into effect in 2018. So we thought that if we are able to create a crowd monitoring system in which there is no way to tell whether an identifier corresponds to a specific individual or to a totally different person, then the problem is solved. This notion is commonly known as anonymity, and it is a powerful means of achieving privacy. This vision is also shared by privacy regulators, which generally suggest that if data is processed in such a way that it achieves anonymity, then it falls outside the scope of the regulations. We propose thus as contribution a novel anonymization technique built on k-anonymity principles, which anonymizes detected individuals immediately at the sensor, while achieving high accuracy when dealing with realistic pedestrian flows within crowds. We model a crowd monitoring environment in the following way. We have a set of scanners acting as a sensing infrastructure. These scanners can be either access points, Wi-Fi sniffers, any sort of machinery which can collect signals from mobile devices. We are splitting the time in epochs of a fixed length, such that we can have a coherent basis for providing insights. Individuals are detected by scanners across these epochs, along with the identifiers of their devices. So for each epoch, we will end up having a set of collected identifiers, a so-called detection set. So far, so good. As we stated earlier, no data should leave the scanners without being anonymized first. So at the end of an epoch, a detection set undergoes a process P through which identifiers are manipulated in such a way that a multiset results. A multiset is like a set, but in which elements can appear multiple times, that number of occurrences being known as multiplicity. Please note that by dealing with a multiset, we allow the existence of many-to-one relationships between individuals and identifiers. This is a fundamental requirement for going away from unique associations. We will return to this process in just a minute. So, only after this anonymization process, data can leave the sensor and be stored in a database. There, crowd monitoring queries can be launched on the resulting anonymized data. Two main types of queries can happen. Simple queries are the ones asking for the size of the crowd sensed by one of the scanners during a particular epoch. To answer it, we would simply need to look at the multiset PD generated at that point. Another type of query we might have is the composite query. This one asks for the number of people that were detected by a scanner in an epoch, by another scanner in another epoch, and so on. Basically, this is the type of query that can capture crowd flows. To answer it, we would need to look at the intersection of the multisets from the corresponding scanners and epochs. A quick mention, an intersection of multisets keeps the common elements along with their minimum multiplicities. Let's now get into the details of the anonymization process that we have been discussing about. Simply having a many-to-one relationship between individuals and identifiers is not enough. We need to be able to offer some guarantees that a certain level of anonymity is achieved, no matter what crowd monitoring query is asked to the system. This is why we introduce detection k-anonymity. What it basically says is that in order for an anonymization process P to be detection k-anonymous, whenever it is applied on no matter what set of identifiers, the resulting multiset should not contain any identifier with multiplicity lower than k. Similarly, a query, be it simple or composite, is detection k-anonymous if the underlying multisets obey the same condition. What is extremely interesting about this metric is that detection k-anonymous simple queries can only lead to detection k-anonymous composite queries. In other words, it is enough to apply such an anonymization process on detection sets in isolation at the sensors, and the anonymity of individuals will be preserved no matter what query might be launched in the future. There is a detailed proof of this in the paper, but the reason is quite simple. The minimum of two numbers, both greater or equal to k, will be as well greater or equal to k. Another metric that we introduce is L-surjectivity. The reason for doing it is that we want to make sure that the many-to-one mapping is real and not only apparent. Imagine a process which simply takes each identifier and makes k copies of it. It would be detection k-anonymous, but it would actually mean nothing. We do not want that. So L-surjectivity says that any anonymized identifier corresponds to at least L real devices sensed by the system. In other words, P should map at least L different devices to the same anonymized identifier. Please note that L-surjectivity is a metric which is achieved across the system rather than being built on purpose at the scanners. It should hold for any anonymized identifier in the whole database and the minimum value of L should be K. Nevertheless, the higher the better. Now, we move on to the next part, where we discuss about how we actually build a detection K-anonymous process P. In our construction, we employ 3 layers of mechanisms. As a first layer, we apply pseudonymization. We already know pseudonymization alone is weak, since it simply does a one-to-one mapping of identifiers, but it is important to apply it in order to strip the identifiers from any connection with their original meaning. Next, on top of it, we apply a truncation operation which cuts off some bits from the identifier. This truncation already makes it possible that more identifiers are mapped to the same truncated one. It can even achieve detection K-anonymity by itself, depending on how many bits are removed. But however, an additional correction mechanism is needed as a third layer. Why do we need it? Because in order to guarantee detection K-anonymity solely by truncation, we would need to remove a high number of bits from the original identifiers. For simple queries, this wouldn't be a problem, because the count on the anonymized data remains the same. But for crowd flows, where the count is performed on an intersection of multisets, the accuracy will be severely impacted, as we can see in this example experiment. And by accuracy, we mean how far the answers are from their original values when applying the anonymization process. Here, we would need to remove all but 5 bits to be sure that all the resulting truncated identifiers appear at least K times. What we would like is to keep a higher number of bits when truncated, moving more to the right side of this graph, where we can achieve a higher accuracy. But this would leave us with identifiers breaking detection K-anonymity. This is why we need to take care of them through a correction mechanism. What does this correction mechanism do? Well, the correction mechanism keeps as they are the truncated identifiers which occur at least K times. At the same time, it singles out the ones that occur less than K times and sorts them in the ascending order. Out of them, it only keeps the first 1/k of them and makes each of them occur K times. This correction mechanism proved to be the one keeping the accuracy of queries as high as possible. There is a clear reason behind it. It has to do with applying this mechanism consistently across the system, ending up with added identifiers, balancing the removed ones, even in the case of intersections. But you can find out more details about this in the paper. Finally, this correction ensures detection K-anonymity for each query. So far, so good. But how does it perform when dealing with crowd flows? Let's start by getting a better view of how we actually model crowd flows. Visualizing crowd flows, we would expect something like this. What we see here is a number of people delimited by a dashed line, and these people are identified as being together at a certain point, and they are also detected later as they travel. This is an ideal case when all of them continue on the same path. However, in reality, there are people leaving as well as joining a crowd flow. So we end up with variations of crowd flows, which much more look like this. Lambda gamma crowd flows, where lambdas stand for percentages of leavers and gammas for percentages of joiners. These characteristics of a crowd flow, together with the parameters of the anonymization process, influence how accurate the answers to the queries are. Having said that, let's have a look at some evaluation results from a simulated environment where we could play ourselves with all these parameters. Here, we cut all but the last 11 bits from the identifiers, and we look at k equals 2, 3, and 4. We start with a crowd of 1,000 people sensed by a first scanner. We want to see the impact of people leaving the crowd before they reach a second scanner. So we fix the percentage of joiners to 20% and range the leavers from 0 to 100%. The accuracy slowly decreases as long as there are enough people remaining in the crowd flow. It decreases abruptly when there are more people joining the crowd flow than remaining in it. But at that point, we are not looking at a realistic crowd flow anymore. We are actually dealing with different crowds mixing together. We can also see that as the demanded K is higher, the accuracy is a bit lower, which means that for better privacy, you have to pay some price in accuracy. In the second figure, we display another experiment in which we start again with a crowd flow of 1,000 people, but this time we are interested in seeing the impact of people joining the crowd flow. So we fix the percentage of leavers to 20% and range the joiners between 0 and 600%. We interpret the results in the following way. The accuracy stays above 0.9 as long as the remaining crowd is larger than the number of people joining the flow. It can go as low as 0.8, please note the y-axis, when there are 6 times more people joining the crowd than they were originally in it. So this means 6,000 more people joining the crowd. Good. Another part of our evaluation takes place in a different type of environment, in which we reproduce real-life deployment settings. To understand how people travel inside the public underground network, in 2016, the London Underground Company performed a pilot Wi-Fi data collection in 54 stations. Later, in 2019, they extended this across the whole underground network. As privacy protection mechanisms, they used instances of pseudonymization, this generating a lot of discussions in the media, along with many negative reactions. The interesting thing is that their purpose, which is understanding how people circulate between stations, can be easily matched to our k-anonymous crowdflow solution, improving the privacy guarantees from pseudonymity to anonymity. Let's see how. Straight from the published reports, we were able to identify 4 types of routes. These 4 types differ by the layout of the crowdflow source and destination platforms, which could have either one or more lines passing through them. This has a word to say on the leavers and joiners parameters of the crowdflows. Let's see now how these types of routes resemble our crowdflows. We make a couple of assumptions regarding the number of people on the trains and on the platforms. They are based on figures found in the published reports as well. Then, by calculating the percentages of leavers and joiners, the resulting crowdflows, as we have defined them in our system, would be a 50-50, 50-200, 80-20, and 80-80 crowdflow. In terms of accuracy, this is how the 4 scenarios perform for different values of k. These results would be achieved using the already existing infrastructure as it is currently deployed in the London Underground network. The impact our anonymization process has on the first 3 types of routes is low. For the 4th type, we cannot accurately capture the crowdflow by using existing infrastructure alone. The reason is that we are trying to identify a relatively small crowd in relation to an overwhelming number of leavers and joiners. However, this can be seen as a desirable result as well, since the system protects the anonymity of people in small crowds by offering lower accuracy in those cases. If we really want to capture this situation accurately, there is a solution at hand, which is augmenting the already existing infrastructure with scanners placed directly on trains. So there is a solution for this. To conclude, we have presented a lightweight anonymization process for crowd monitoring infrastructure, which can be applied directly on the sensors in isolation before any data is handed out to a server. By applying this, the privacy of each monitored individual is preserved under detection K anonymity guarantees. At the same time, we have shown that high accuracy can be achieved for situations resembling relevant cloud flows. Future work includes a practical implementation to be installed on scanners, as well as deploying it within an actual crowd monitoring system. Thank you for your attention. I would be happy to respond to your questions now. Thank you.
Hello everyone, my name is Yifan Du. I come from Paris, France, and today I would like to make a presentation on our paper. It's called IM, Interpolation and Aggregation on the Move, Collaborative Crowdsensing for Spatio-temporal Phenomena. My presentation will follow such an outline. First, I would like to introduce the crowdsensing, the challenging crowdsensing, what crowdsensing is used for, and the related work for crowdsensing. Then, in second part, I will present our previous work, which motivated us for such a IM work. And then I will introduce in detail our IM solution, the implementation algorithm, and so on. Then the evaluation will show how the IM solution overcomes the challenge. Finally, I will make a conclusion. So our topic is about mobile crowd sensing. The crowd sensing can be considered as a ubiquitous data source. Some people call the crowd sensing citizens as sensors, and it has three components. First, there are people or citizens, and these people they have mobile devices or smart devices like smartphone, tablets, or smartwatches. And there is also the server on the cloud which is responsible for the everything, and we call people and the smart device together as crowd sensors. The crowd sensing has two types. The first one is participatory, and in this type it requires the proactive involvement of people for the contribution. And our focus is the other type, which called opportunistic crowd sensing. The smart device collects sensing data in the background, and it does not require any action from the users. And what does the opportunistic crowd sensing sense the application scenario? For the participatory one, it's the knowledge from the people. And for our opportunistic crowd sensing, we focus on the phenomena around the people. So there is our application for the environment monitoring of the smart city. Precisely, it's noise pollution monitoring using the microphone of the smartphone. The application is called MBCity, which was developed by our team, and it collects the noise level, the sound level of the city. It creates a city map of the noise pollution, and it can plan the paths depending on the sound level. There is always a efficiency challenge in the crowd sensing. First, there is a data quality problem because of the different device sensing contexts. And in this work, we focus on the spatial-temporal sparsity and the uneven distribution of sensing data, because the crowd sensing depends on the mobility of the people. So there is a spatial-temporal problem. And the second one is about the sensing cost challenge. There is a cost on any device, and in this work we focus on the resource cost on the cloud servers. The server on the cloud, which is often paid by the organizer of a crowd sensing platform. To achieve the efficiency of crowd sensing, there have been three kinds of work for the context awareness to enhance the measurement of the crowd sensing management to enhance the workflow of crowd sensing, and we have conducted previous work in the two aspects. And in this work, we focus on the data processing. For the data processing, there is a collection for, and specifically, we focus on the data analysis and the post-processing for the crowdsensing to achieve the efficiency. Most traditional state-of-the-art work, they are mostly centralized solutions, and we want to promote the decentralized solution, which is good for the privacy and for the load balancing on the cloud and so on. Our general solution is a transition from the cloud to the edge. From three perspectives. In the computing perspective, nowadays the smart devices, they are becoming more and more powerful. They can perform complex computation. And in the networking perspective, we have multiple network interfaces, including the cellular network to the base station and also device-to-device communication, such as Wi-Fi Direct and Bluetooth. Of course, for the crowd sensors, there is a human perspective. We have social behaviors of the people. It can be the interaction among people and the human activity context and so on. In our previous work, we have been working on the collaboration of crowd sensors. We have promoted the group-wise collaboration. The idea is to leverage the mobile ad hoc network to support teamwork among crowd sensors to enhance the efficiency for data collection. And our previous work of group-wise collaboration discovers the right neighbors to be the group and to share the workload within the group members. But the solution is not enough. It should be more robust from the stable groups to brief encounters. Although a collaborative group called sensors is good and efficient for data collection, but it works only good for the dense and community scale because the group members should stay together and share workload for data collection for a while. And in other scenarios, what if the people are traveling very fast across the city? It's a kind of sparse and urban scale where people don't stay together. So we can still use the same framework for discovery and collaborate, but there is no longer stable groups. That's why we introduced our solution of IM, which is collaboration in the data analysis phases, and it happens via the momentary encounters. The data analysis focuses on the spatial-temporal measurements. So what is the general data analysis for our spatial-temporal crowd sensing? It includes both interpolation and aggregation. The interpolation is to deal with the sparsity in the time and space domain of our data, and the aggregation is to deal with the multiple measurement on overlapped cells. Finally, the interpolation and aggregation help to generate a state map of the noise pollution. So in our previous implementation, the post-processing happens on the cloud server. It assumes that every crowd sensor should upload the data to the cloud, and the cloud will perform the analysis on the entire dataset. This introduces the cloud budget problem, which is paid by the crowd sensing organizer. Then we propose the IM solution, which is a distributed data analysis. This figure shows the system design. The principle is that every device performs the pre-processing. So every crowd sensor, it processes a portion of data on itself. And then the processed results will be relayed from one device to another, from one cloud sensor to another, and finally to the cloud. We can call it interpolation mediated aggregation. And in this figure, we can observe that each cloud sensor, each smart device performs the sensing, preprocessing, and the interpolation. When it meets another cloud sensor, it performs the relay and aggregation. And finally, there will be some device upload the data to the cloud, and the cloud only performs the aggregation, storage, or visualization for the clients. This system has two main problems to be solved. The first is about the aggregation decision. It should be smart. When there are two cloud sensors encounter, we must make a decision on the aggregation. At each encounter, our algorithm is based on the data quality. In principle, when two cloud sensors meet, they exchange the data and they decide the one cloud sensor as the mainstay. The mainstay will aggregate the two results, and the mainstay will carry the result for next relay. Our algorithm, based on the data quality, foresees more future encounters. Because the more you encounter, the more data you have, and the better your inference, your interpolation quality will be. And the second problem to be solved is how do we aggregate two inferences. We say that each cloud sensor performs interpolation, so they both have its own interpolation, its own inference. And when they meet, they should aggregate the ground truth. They should aggregate the ground truth over inference, but they should also aggregate two inferences. Here we applied the generalized product of expert based on our Gaussian process regression. The Gaussian process regression is our model for the interpolation. It's a very general machine learning model. So we have a aggregation on the average and also on the variance to give more accurate results of aggregation. This figure shows the overall workflow of our IM solution. Each cloud sensor sends, interpolate, and store the data in local tensors. The cloud sensor will discover other cloud sensors, and when they meet another cloud sensor, they will exchange the data, and they will negotiate a mainstay. The mainstay will aggregate the data into one. Then the mainstay will carry the data and keep such a process for next aggregation and relay. Finally, the mainstay which maintains the data will upload the data to a cloud for aggregation and database. This figure also shows the process of the cloud sensor on cloud sensor. So we have the data on cloud sensor, we perform the pre-process for tensor, we do the interpolation, and we aggregate when we meet another. We have a protocol implemented using Python 3 on the device, and the prototype is also available on the GitHub. We have performed the evaluation on using our dataset from 1 year observation over Paris and from 550 cloud sensors. First, we have evaluated the interpolation and aggregation. We compared different interpolation approaches, and we found that Gaussian process regression with Martin kernel is the most efficient in execution time, especially it must run on the device. And also, Gaussian process regression with Martin kernel is robust for the interpolation accuracy. For the aggregation, we have compared our opportunistic aggregation with ideal and iterative cases, and also with the stochastic cases without the smart decision. It shows that our aggregation approach ultimately achieves the best accuracy. So, in general, constant process regression is efficient for interpolation, and our opportunistic aggregation is the closest one to the centralized one in accuracy. We also run the prototype on device to see how the cost, how much is the cost on the device. So the energy consumption on the device is not very much because the aggregation is very light and interpolation is only once. We also introduced more relays from peer-to-peer instead of uploading to the cloud. The execution time on the device is very different from interpolation to aggregation. In general, our opportunistic aggregation is feasible on device. The interpolation occurs only once, and aggregation is very light and it's linear. So we have a more peer-to-peer or we call device-to-device aggregation and relays. Finally, on the cloud, the cost is significantly reduced because the cloud only performs simple aggregations. Compared to centralized one, our distributed interpolation and aggregation makes the server execution time to a very low level, and the upload to the cloud is also reduced significantly because we have more peer-to-peer relays. And finally, the budget on the cloud server is reduced because we have less cloud computing, we have less network traffic to the cloud. So the resource cost on cloud is very limited. The cloud only does linear aggregation, and there is less upload and lower budget. In conclusion, we believe that crowdsensing is a good way to achieve ubiquitous environment monitoring, and crowdsensing have many potential applications, such as pandemic monitoring in recent situation. And our contribution in this paper is a pairwise collaboration for crowdsensing data analysis, especially for the spatial-temporal sound level measurement. It occurs between encountered crowd sensors in a sparse and urban area. What our approach achieves is a lower uploading cost, less cloud computing, and thus lower budget. It's a shift from the cloud computing to the edge computing. Here is our previous work and on the collaborative crowd sensing as a reference. So thank you for your attention.
Hello everyone, I welcome you all and thank you for showing your interest in our research. I am Subhash Sagar, currently a PhD student at Department of Computing, Macquarie University, Australia. In this particular paper, I will talk about a time-aware machine learning-based trust revelation model for social Internet of Things. This paper is accepted in main track of MobiQuitous 2020. This is the outline that I will be going through as the presentation progresses. You will encounter all these topics including introduction, research contribution of this paper, followed by the proposed trust model, simulation results, and finally the summary of this paper. In introduction, I will briefly talk about the definition of Internet of Things, social Internet of Things, and a high level overview of our proposed model, followed by the some basic definition of trust in social Internet of Things and why we need trust in social Internet of Things. So, as we all know, Internet of Things have influenced our lifestyle from the way we react to the way we behave, and it is the network of billions of devices with sensing capabilities connected to the Internet. As these billions of devices are connected to the Internet, there are many research challenges. including but not limited to the scalability issues as the devices are keep on increasing over the years, service discovery issues, and service compositions, etc. Recently, a new paradigm has emerged known as social Internet of Things. Social Internet of Things is nothing but the combination of social networks and Internet of Things, where each object is capable of establishing social relationship with other objects autonomously according to the rules set by their owners. You can see in this figure some of the common relationships that objects can uh, establish during the interaction or during the communication. Starting with the co-owner relationship, the co-owner relationship represents the objects belonging to the same owner. Social relationship is the when two people two owners come into contact with each other, their devices also come into contact with each other, and this type of relationship is called social relationship. Parental object relationship is the when objects from the same manufacturer, like the same company, when they interact with each other, they establish the parental object relationship. And finally, the co-location and co-work object relationship, the objects from these kind of relationship are established when objects from the same working location interact with each other. This is the a high level overview of our proposed trust model. Here we can see on the left side of the figure, a bit explains how social Internet of Things work. Here we can see so objects and humans are maintained at two different levels. The reason to maintain at two different levels is to facilitate the owners to set the rules for protecting their privacy. And on the right side of the figure shows a basic overview of how an object is computing the trust of another object. For example, in this figure, object A is computing the trust of an object trustee B by following the three simple steps, starting with the request from the social profile request of an object or a trustee from the server. This will give the information of the number of common friends between the truster and the trustee, whether they are related to a different kind of relationships, how they are, whether they are cooperating with each other or not. These social object profile will be requested from the server. And the second step after requesting the social profile, the second step is the interaction between both the truster and the trustee. And finally, after the interaction, the truster evaluate the trust of the trustee or the object B and update the trust through the local authority. As we have already discussed, that the social IoT is the merging of physical objects, cyber components, and most importantly humans as well. This kind of merging introduces new concerns of privacy, security, and trust, and most importantly the communication link between the objects and between the humans is more exposed towards external and internal attacks. Here, by external attacks are the attacks initiated by the unauthorized nodes in the network, and we already have the solution for these kind of attacks, that are cryptographic and authentication techniques. And the second one is the internal attacks. These are the attacks that are launched by authorized nodes that have valid credentials. It means they have already bypassed the traditional security measures. In this type of attack, the security solution does not work. For that, it means we need a different solution, that is to establish or design a trust evaluation model. Overall, trust in SIoT is referred as the notion of belief or confidence of truster in a trustee or one object into another object to perform a specific task in a specific context within a particular period of time. Till now, I have already discussed the importance of trust in social Internet of Things. The main contribution of this paper are threefold. At first, we have proposed a time-aware trust evolution model that utilizes different relationships and cooperativeness among the objects, and further tackles the misbehaving objects in the network whose status changes over the period of time. To get the unified trust score, we have proposed a machine learning driven aggregation in compared with the traditional weighted sum method that has some disadvantage that I will discuss in later slides. And the final thing, and finally, we have evaluated our proposed model in a simulation environment at different time instances in order to observe the change in the trust score of an object and the effect of different features or different relationships on the trust score of an object over the period of time. This figure shows the steps involved in our proposed trust evolution model. As can be seen in the figure, the first step to compute the trustworthiness of an object is to get the social information of the trustee. As can be seen on the left side of the figure, that has object social network, where each object shares their social profile in terms of friends, interest group related to the community of interest, co-work relationships, etc. Subsequently, the next step is to extract the trust features or trust metrics from the information provided in the first step. Feature extraction components are specific to different SIoT applications, and the designated trust features for this paper that are selected are friendship similarity, community of interest, co-work similarity, and cooperativeness. I will talk about more detail of these features in the coming slide. Finally, the main objective of this paper is to evaluate the trustworthiness of an object. So the last step is the computation of trustworthiness of an object. This trustworthiness of an object is computed using both the direct trust. Direct trust represents the direct perception of the truster towards the trustee, and the reputation of the trustee in the network. The second step in the trust computation component is the aggregation of all the trust features that are extracted in step 2 to get a unified trust score or a single trust value. Finally, the trust decision component provides the information on whether a node is trustworthy or untrustworthy based on some threshold values, and those threshold values are also application dependent. Like we can use whether if the value of a particular object is greater than 0.6 or 0.7 in the range, if the range of the trust score is from 0 to 1, then those nodes are said to be trustworthy and remaining nodes are said to be untrustworthy. In this slide, I will talk about the a bit detail of the selected trust features, starting with the friendship similarity. Friendship similarity signifies the importance of an object locally among its neighbors at any given time t, and is computed as can be seen in there if two objects, object OI and OJ, are communicating with each other, and object OI wants to compute the trust of an object, it will first compute the friendship similarity of that particular object, and is computed as the ratio of common friends between the object OI and object OJ to the ratio to the total number of friends among these objects. Friendship similarity prohibits the malicious objects from establishing counterfeit friends in the network to get the advantage over the other nodes in the network. Similarly, covert similarity gives the notion of trust where two or more objects collaborate with each other to accomplish a common goal. So we have utilized the concept of multicast interactions, and covert similarity is computed as the common multicast interaction, the ratio of common multicast interaction between the object OI and OJ to the total number of multicast interactions. Community of interest is similar to the friendship similarity. In community of interest represents the community-based trust feature where both the objects share common interest group like social groups or e-commerce, etc. and is computed similarly to the friendship similarity, is computed as the ratio of common interest group between the two objects that are OI and OJ to the total number of groups where both the OI and OJ are involved in. Finally, the important of all is the cooperativeness among the two participating objects. Cooperativeness represents the measure of balance in the interaction between the object OI and object OJ. So we have utilized the concept of entropy. That formula is given. This shows the concept of entropy to compute the cooperativeness. The TP in this formula represents the successful interaction divided by total number of interaction among the participating objects. This cooperativeness is basically it's measured at all these trust features are measured at different time instances. After extracting all the selected features, the next step is to aggregate those features to get a single trust score. Here in this formula, the aggregate total trust is equal to the sum of all the trust features that are extracted in the previous slide and multiplied by the WI that represents the weight of each individual feature. Normally in the literature, most of the literature use the weighted sum approach to combine all these trust features, but weighted sum approach has many disadvantages, including how to select the weight for each different feature at different particular time and for different applications. So there can be infinite number of combinations. To overcome the challenges of weighted sum approach, we have utilized the machine learning driven aggregation scheme. So machine learning driven aggregation has two steps. First step is the clustering to label the data, as the data that we have used in this for this paper for the evaluation of our model is not labeled, so we have used clustering first to label the data, and after that we have used a multi-class classification algorithm, that is random forest algorithm, to identify the best decision boundary to segregate the trustworthy and untrustworthy node. And additionally we have also find the get the information of importance of each trust feature in terms of its weights. Then we utilize those importance in terms of weights to get a single trust score. As there is no directly available data for the SIoT environment, so we have used the SIGCOMM 2009 conference dataset that comprises of the trace that could be mapped in the form of SIoT environment. This particular dataset contains 76 nodes and 18,226 interaction among these nodes for over a period of 4 days. So the trust features are learned for each pair of nodes with at least one interaction among them. So we randomly took 20 nodes over a period of 24 hours to observe the behavior of these nodes at different time instances. And the feature matrix that we use is represented in the form of a matrix where each row represents each feature that is computed using the formula that we have discussed in the previous slides. Here the M shows the number of interaction among these nodes. As we have selected 20 nodes, it means we have total number of 400 plus interactions. For machine learning based trust aggregation, we have used clustering and classification. After extracting the features as we discussed in the previous slide, for demonstration purpose, we have took 2 pairs of nodes at a time to just to demonstrate, just to visualize how the clustering is dividing the interaction in terms of trustworthy and untrustworthy. Here in the first row we can see how the clustering has divided these interaction in two categories. Similarly, in the second figure we can see how the random forest classification has given the best decision boundary to segregate between these trustworthy and untrustworthy interactions. After the machine learning based aggregation, that is after clustering and classification, the trust score of 20 nodes over the period of time is shown in these figures. Here we have highlighted two nodes, that is there are node 8 and node 19. Here we can see the trust score of node 8 is increasing over the period of time, while the trust score of node 19 is decreasing over the period of time. We will show in the next slide like why the trust score of these two nodes are increasing and decreasing. Here we can see the reason of why trust score of node 8 is increasing. As we can see in this figure, the features for community of interest and co-work similarity of node 8 remains the same, but the cooperativeness and friendship similarity of this particular node increase over the period of time. That's why the trust score of node 8 increasing. Similarly, for node 18, all the trust features, community of interest, cooperativeness, friendship similarity remains the same, while co-work similarity of this particular nodes decreases. That's why the trust of this particular node decreases. We have evaluated the performance of proposed model in terms of precision, recall, and F score. As we can see, we have two classes, trustworthy and untrustworthy, and the accuracy of our model is around 99%, and we can see achieve the all the high precision, high recall, and high F score for both the classes that are trustworthy and untrustworthy. So overall, we will propose and investigate time-aware trust evaluation model by utilizing characteristic of an object in terms of its friendship similarity among the other nodes, community of interest, co-work relationship, and cooperativeness. And subsequently, we have used machine learning based approach to synthesize these trust features to get a single trust score. And finally, the simulation results demonstrates the trust of an object evolve over the period of time and with respect to the different trust features as well. In the future, we intend to design an attack model to further verify the accuracy and convergence of our model, and we will also compare our model with the some related model that are already present in the literature. Thank you. That's all. If you have any further question, you can contact me on this email, or if anyone wants to collaborate with our research, you are most welcome. Thank you very much.
Hi, I'm Vasish Dudu and I'm currently a graduate student in the University of Waterloo. This work, titled Quantifying Privacy Leakage in Graph Embeddings, was done while I was at Inria's Privatics lab in INSA, Lyon, working with Professor Antoine Boutte and our collaborator Virat Shejwalkar from UMass Amherst. Here's an overview of this talk. I will give a basic introduction to graph embedding techniques and give a detailed background on the learning algorithms and the privacy risks that are associated with machine learning. I will then give the detailed attacks that we use for leaking private information from graph embedding algorithms before concluding my talk. So several large-scale real-world systems are modeled in the form of graphs, and these non-Euclidean data capture the links between nodes in addition to what is being captured by Euclidean datasets, for which traditional machine learning models have been proposed. However, traditional machine learning models cannot process such large graph data, and in order to address this problem, graph embedding algorithms have been proposed which capture these low dimensional representation of the large graph data. The embeddings are trained in such a way that they capture the original graph semantics and can be released for further processing, such as in the case of recommendation systems. One such case is that of graph neural networks, where the embeddings can be taken and used for several downstream tasks such as link prediction, node classification, clustering, and network analysis. And graph neural networks have shown state-of-the-art performance in all these cases. The questions that we ask in this work are: what are the privacy risks that are associated with releasing graph embeddings, and what are the privacy risks that are associated with downstream processing tasks of embedding. So I will go over some background concepts in order to make the rest of the talk very clear. So the first concept that we look at is graph learning, where graph learning techniques typically rely on message passing algorithm. And this message passing algorithm allows to aggregate the features of the neighboring nodes in order to predict the class of the node in question, or estimate what the features or approximate features for the particular node are. And these models typically map embeddings map the embeddings to an output probability distribution, which indicates the likelihood of the input belonging to different classes. And we specifically focus on inductive training of graphs where the test nodes are unseen during training. And in order to do that, we sample a subgraph for training the models and evaluate the trained model on a non-overlapping held out graph. This is an important assumption for privacy leakage, which allows the adversary to learn new information given some prior knowledge. So privacy attacks have been considered before in the machine learning literature, but for the specific case of Euclidean dataset, and as a result, no work exists to quantify the privacy risks associated with graph learning techniques such as graph embedding algorithms and graph neural networks. So a privacy violation in machine learning is said to occur if an adversary infers something about a particular user's record in the training dataset which cannot be inferred from other models trained on similar data distribution. And this allows us to quantify privacy risks using three main attacks, one being the membership inference attack, the data reconstruction attack, and attribute inference attack. We extend these privacy attacks to understand the privacy risks that are associated with releasing graph embeddings for downstream processing tasks, such as graph neural networks. So the first attack that we consider is that of membership inference attack, where the goal of the adversary is to infer whether a given data point was part of the training data of the model or not, based on either the output predictions for that particular input or the embeddings corresponding to that particular input. In this particular setting, we assume that the embeddings are generated using a graph convolution layer, and these embeddings are then accessible to the adversary. The second case that we consider is that where these embeddings are then passed through another convolution layer to generate the output predictions for the nodes, and these output predictions are accessible to the adversary. The attacker exploits the notion that these graph learning algorithms typically overfit and perform better on the training data compared to the testing data. And as a result, the prediction scores corresponding to the trained data are significantly different from that of the test data. And similarly, the embeddings for the members and non-members of the trained data are also distinct. Keeping these distinctions in mind, the adversary can then train an attack model, which will then predict whether a given data point that is sampled from the same distribution as the training data is part of the training data or not. So there are two important privacy implications for membership inference attack. The first is that it violates the individual's privacy. So if we consider a graph capturing the spread of a disease, and an adversary can then infer whether or not a user's data point was part of the training data or not, then the adversary can eventually infer the health status of that particular user. This can have other secondary side effects, including problems with regards to insurance, jobs, and other social benefits. The second privacy implication to this attack is that the training data is an important intellectual property for the company, which is used to design high quality state-of-the-art architectures. In case of membership inference, when used iteratively, could allow the adversary to reconstruct a part of the sensitive training data and hence violating the intellectual property of the company. So here we consider the membership privacy leakage from embeddings, and we see that the embeddings for members and non-members for the training data of the graph embedding algorithm is distinct. And in order to exploit this and distinguish or train an attack model to distinguish between them, the adversary considers this problem as an unsupervised attack problem, where the adversary trains an encoder and decoder to map these embedding vectors to get a single membership values to get a single membership value. These membership values for all the embeddings are then clustered to form a cluster for that corresponding to the members of the training data and those corresponding to the non-members of training data. And the adversary here has some prior knowledge for small number of data points and their corresponding cluster mappings, so that he can identify which cluster lies for the training data points and that for the testing data points. The metric that we consider here is the advantage that the adversary has in successfully identifying whether or not a given data point was part of the training data or not. And since this is a binary classification problem, any accuracy beyond random guess of 50% indicates a leakage from the model. And this accuracy beyond 50% is then scaled between 0 to 100 to obtain the inference advantage. We find that for 4 different state-of-the-art architectures that we consider trained on 3 different data sets, we find that the inference advantage is as high as 36% beyond random guess. Now we consider membership privacy leakage from the output predictions, where the adversary has only access to the output predictions of the model, and based on which the adversary has to infer whether or not a given input was part of the training data or not. As seen in the diagrams, the cross entropy loss distribution for the members and non-members are distinguishable, and this allows the adversary to have an advantage to perform membership privacy attacks successfully. Secondly, we can also see that the data points, the members of the training data, are predicted with a very high confidence by the model as compared to non-members of the training data, which have confidence scores distributed across all classes. In order to exploit these differences, we propose 2 attacks. The first one being shadow model attack, where the adversary trains a shadow model to mimic the target model performance using a substitute training data sampled from the same distribution as the victim model's training data. Here, the adversary trains the attack model to distinguish between the members and non-members by querying the shadow model and identifying the features which help distinguish the members from the non-members. This attack leaks membership status with 15% inference advantage on average across all the 3 datasets that we considered. We then look at the confidence score attack, which exploits the idea that the model is more confident on seen training data compared to unseen test data. Here, the adversary chooses a threshold and looks for the maximum confidence across all classes, and if the maximum confidence is greater than the threshold, then the adversary predicts the input data point as being part of the training data. This attack leaks membership status with 28% inference advantage on average across all the 3 datasets that we considered. Next, we want to understand the influence that neighboring nodes have on membership inference of a particular node in the network. In order to study this, we exploit the message passing algorithm's ability to aggregate features from neighboring nodes, and we increase the range of aggregating features from neighbors by increasing the number of layers in the network. Here we find that the leakage and prediction accuracy decreases on increasing range of message passing algorithm, and the reason this happens is because of the over smoothing of features due to aggregation across a larger number of nodes, which reduces distinguishability, which is important for not only high prediction but also to distinguish between members and non-members. To summarize, the membership privacy is influenced by the structured data and the preferential node connections. Next, we consider the second attack, which is the graph reconstruction attack, where the question that we pose is, can we reconstruct the target graph from released target graph embeddings? So here the setting that we consider is that the adversary has some prior knowledge about an auxiliary subgraph and the corresponding embeddings, and trains a graph encoder decoder model to map the auxiliary subgraph to the corresponding embeddings and map these node embeddings back to the subgraph, and making sure that the auxiliary subgraph and the reconstructed subgraph are close to each other. Once the training is completed, the adversary takes the decoder to map the release target node embeddings to generate the approximate target graph. An implication of this particular attack is a link inference, where an adversary can infer a potentially sensitive connection between any two nodes in the graph. This attack has two main privacy implications. The first being that the graph data is an intellectual property of the company, using which the companies design state-of-the-art architectures, and this intellectual property is violated when the adversary is able to reconstruct the target graph data using just the embeddings. Second, these embeddings are considered to hide the structure of the network and the participant-sensitive attributes, and through this attack, we show that we can reveal both the structure as well as the participants in the training data. In order to estimate the performance of graph reconstruction attack, we consider three metrics. The first one being the AUC-ROC score, which is area under the ROC curve, which gives us how good a model is to distinguish different classes. The second is the average precision, which estimates the percentage of the predicted samples which are actually part of the target graph. And finally, we consider the attack accuracy, which for a binary, specifically for link inference attack, which is a binary classification problem, and any accuracy beyond 50% random guess indicates successful link inference. For graph reconstruction, on the three data sets, we find that the adversary is able to successfully reconstruct the target graph with a high AUC-ROC score as well as high average precision. For link inference, we see that all the data sets leak with accuracy greater than 50% random guess. Finally, we consider the attribute inference attack, where the goal is to infer sensitive node attributes from released graph embeddings. We consider the setting where adversary has embeddings for some of the nodes and the corresponding sensitive attributes. This is a practical assumption that is typically seen in social networks, where some of the profiles have some of the sensitive attributes publicly available, while there are other profiles which do not put their sensitive attributes on public domain. The attacker then trains a supervised attack model to map the embeddings to sensitive attributes. And in this work for evaluation, we consider two state-of-the-art embedding algorithms for graphs, namely DeepWalk and Node2Vec, trained on datasets, trained on Facebook and Last.fm datasets to infer gender and location as sensitive attributes respectively. An important privacy implication of this is that it allows the adversary to infer sensitive attributes for users with private profiles on social networks using the data that is available from public-facing profiles. In order to evaluate attribute inference attack, we consider F1 score as a metric, which is the harmonic mean between precision and recall, and estimates the percentage of samples in a target graph which are predicted correctly as being part of the target graph. As part of the results, we see that the F1 scores indicate significant attribute leakage from embeddings, and we also see that an increase in adversary knowledge results in a small increase in attack performance as well. The attack is based on the intuition that neighboring nodes in a graph are mapped to similar embeddings, and these neighboring nodes are likely to have similar attributes, which can be inferred using attacks such as attribute inference attacks. To summarize, this paper explores different privacy threats associated with graph learning algorithms, specifically on releasing graph embeddings and post-processing techniques such as graph neural networks. We quantify these privacy risks using three main attacks, one being membership inference attacks, a graph reconstruction attack, and finally attribute inference attack. As part of potential mitigations, we discuss four approaches. The first being the lowering the prediction precision by rounding, which can reduce the amount of information available to the attacker and hence lowering their attack success. This, however, will be followed by a decrease in accuracy as well, and hence a privacy accuracy trade-off analysis is required. Differential privacy and designing differentially private embeddings might also help in identifying the bound on individuals' privacy leakage from both the embeddings and the output predictions. Third is adversarial training, where the models can be trained to maximize performance while minimizing the adversary success. Finally, adversarial examples and adding adversarial noise to the embeddings can be leveraged as a defense mechanism in order to force the attacker machine learning model to misclassify. With that, I would like to conclude my talk, and I thank you for listening.
Good morning, everyone, and thank you very much for your presence. My name is Diogo Vaz. I'm from INESC-ID, Instituto Superior Técnico Lisboa, Portugal, and I'm here today to present the article MIRES Recovering from Cyber Attacks in Mobile Applications with Backend-as-a-Service. And as the title indicates, the work explored the context of mobile applications, because nowadays mobile applications are an important resource used by companies in providing their services, such as banking services or social network services. And generally, these application systems involve an architecture composed of a mobile application installed on the mobile device that interacts with a remote server identified as the cloud. And it was with the growth of mobile applications that several frameworks emerged, allowing to speed up the application's development. Among the solutions, a cloud service called Backend-as-a-Service has emerged as a service that offers a set of features already implemented, such as user authentication and data storage, which can be easily integrated into the application through an API. However, errors in the design and implementation of mobile applications can create vulnerabilities in the applications themselves. For example, a study by Positive Technologies in 2019 found that, of the systems analyzed, 60% of the vulnerabilities were found in the mobile application, and on both Android and iOS, about 2/3 of the vulnerabilities found were of medium-high risk. One example was insecure inter-process communication, where the installation of a malware could access messages between the application components. And when these vulnerabilities exist, exploiting them maliciously can lead to intrusions that will corrupt the state of the application and, consequently, the state in the cloud. And when this happens, it is necessary to have a mechanism that can revert the effects of the intrusion without jeopardizing the other legitimate data, a process that is called intrusion recovery. And it is exactly in this field that our work focuses. We assume that vulnerabilities exist, that they have been successfully exploited, and consequently their effects need to be eliminated from the state of the application. In this presentation, we begin by introducing the objectives of this work, then we present the solution adopted, we debate the evaluation made on the solution, and finally we present the conclusions of this work. The intrusion recovery field has been studied over the years, and that's why we have selected 5 studies that we will present in 2 groups. The first group It's a group of older works, and we can see that all provide the same recovery approach, which is the rollback recovery approach. The rollback recovery approach basically works by reverting the state of the application to protect to a state free of damage, and then re-execute all the legitimate operations in order to bring back the application state to its original state. We can also see that there are two target systems introduced, ML system and web applications. There are also two types of recovery. An offline recovery is a recovery where the normal functioning of the application to protect must be stopped in order to recover its state, while on the online recovery, the normal functioning of the application to recover does not need to be stopped. We can also see that WARP is the only one that provides an user's recovery mechanism, which allows users to recover their own actions, and all of them are based on a proxy implementation. Then we have the second group, a group of more recent works. We can see that both works introduce a new recovery approach. There are compensation transactions. Compensation transactions are new transactions that are generated in order to revert directly the effects of the intrusion. We can also see that a new target system is introduced, NoSQL databases. Both solutions implement an online recovery type. None of them provides an user's recovery mechanism, and NoSQL Undo is the only one that does not need a proxy in its architecture. And finally, in this case, we present MIRES. MIRES uses compensation transactions in its recovery approach. It focuses on a new target system, in this case mobile applications, provides an offline recovery, however it's an offline recovery focused on the availability of the system to protect. It provides a user's recovery mechanism, and finally, like NoSQL Undo, does not need a proxy to work. Therefore, the objectives of this work included the development of an intrusion recovery service for mobile applications that use Backend-as-a-Service, to introduce a new offline recovery model, and to develop a user's recovery mechanism. Based on the objectives, we then developed the MIRES, an intrusion recovery service based on compensation transactions that does not require a proxy. The supported recovery model is divided into two phases, a locking phase and a reconstruction phase, in order to reduce system unavailability during recovery. Also, MIRES offers a client-side recovery mechanism that allows to revert users' actions, making it possible to recover several actions from different users in parallel without blocking the system. The execution of MIRES is supported by several components that can be divided into two groups. The front-end components that work directly in the mobile application, and the back-end components that work in the cloud. The service can be executed in two phases: the normal execution that takes place during the normal operation of the application to protect, and the recovery execution that starts when the administrator decides to recover the state of the application. During normal execution, the MIRES package allows to configure the application by preventing reads to locked documents, that is, documents that cannot be accessed by anyone, and blocked documents, that is, documents that only the last user who wrote upon them can access. As also allows to send a flag associated with each write operation that will help to register the operation in the log. In the backend, whenever a write is executed, cloud loggers capture both the modification in the application's database as well as the flag associated with the operation, and are both analyzed so that the operation is recorded in the log. Then the log can be accessed by the administrator console. There is also the possibility to store snapshots of the database documents during this phase. In this case, this activation is also done by the MIRES package. Regarding the recovery execution, it is initiated by the administrator through the console. Then notifications explaining the recovery are sent to the users and the database is locked where it is possible to read but not to write. Then the blocking phase is performed, where MIRES analyzes the log and identifies the infected documents, locking them directly in the database. When finished, a new notification is sent about the fact that some actions may not be still possible, and the database is opened. Finally, the reconstruction phase is executed where MIRES reconstructs the infected documents in memory and replaces them directly in the database. At the end, a new notification is sent to the users to inform the recovery conclusion. Here we have a small demo of the administrator recovery mechanism, where we have a user already logged in on a social network application. First, we will create a new post, in this case a text post, that later will be recovered by the administrator recovery mechanism. As you can see, the text post was performed and also logged by the MIRES service. Then, to recover this service, we select the transaction, we click on the button, and we define an explanatory message, in this case invalid text. Then we start the recovery process, where a notification is sent to users saying that the recovery process will be initiated, and the database is locked, which means that users can read. However, if we try to create a new post, it will not be possible since the database is locked for new write operations. Then we will continue with the recovery process, and the locking phase will terminate, the database will be opened, and a new notification is sent to the users. In this case, the infected post was directly locked on the database and it cannot be accessed by anyone, and the database will be now opened for new write operations. As you can see, a new text post was executed. Finally, we can conclude the recovery process, where the reconstruction phase is executed and terminated. A notification is sent to the users saying that the recovery was concluded, and on the left side, the administrator will be able to interact normally with its console. In addition to the administrator's recovery, there is also the user's recovery mechanism, which allows users to recover their last performed action. This mechanism is supported by the MIRES package, which we use to define transactions as recoverable. In this case, recoverable transactions will generate blocked documents, that is, documents where only the last user who wrote upon them can access. Whenever a recoverable transaction is executed, the package generates a notification with a button that allows to revert the transaction. When the user clicks on the notification button, the locking phase is performed, where the documents associated with the action are directly locked by the application and the request for recovery is sent to MIRES. When the request is received, the application receives a notification confirming the recovery. Finally, the user's recovery model starts the reconstruction phase, similar to what is done in the administrator's recovery, and at the end, a notification is sent to the user to inform the conclusion of the recovery. If the user does not click on the notification button and consequently does not start the recovery, the user's recovery model will unblock the document, making it visible to everyone. Here we have a small demo of the user's recovery mechanism, where we have two different users logged in on the same social network application. In this case, we will use one of the users to create a new text post that later will be reverted by the same user. As we can see, the text post was executed. The user that executes the post can access the post, however, other users will not be able to access that post, and this is the definition of a blocked document. Then the notification with the button is generated that allows to start the recovery. The mobile application locks directly the infected document and makes it invisible to every user. And then, finally, the reconstruction phase is executed, where the infected post is deleted from the database and the user receives a notification saying that the recovery was completed. Having now presented the execution and operation of our service, we will move to the evaluation made on MIRES. The focus of the evaluation was to verify the overhead in terms of performance and data imposed by MIRES, as well as to verify the recovery times for different scenarios. To achieve that, MIRES was tested in 3 applications: a social network application, a messaging chat application, and a shopping lists application. Regarding performance, we executed 1000 CRUD operations in each application, organized in reads and writes. From these tests, we are able to conclude that write operations increase the overhead imposed by MIRES when compared with read operations. For example, the shopping lists application with 80% of writing was the application that presented the higher performance overhead, around 23%, when compared with the remaining applications with less write operations. However, despite the considerable performance overhead imposed, we think it is acceptable given the benefit. MIRES imposes additional data on the application's database, as well as related to the construction of the log. For example, in the first table, if the application has 1 million users and 1 million documents, MIRES imposes 0.41 gigabytes of additional storage. In the second table, we have the storage needed to log 1 million operations performed in each application when following the model of operations executed in the performance tests. As we can see in both tables, we believe that the storage needed is acceptable when compared with the amount of data that we are storing. To test the recovery process, we simulated different scenarios from recovering one operation to 1000 operations. With the tests, we are able to conclude that to recover one operation, MIRES needs less than 1 second, while to recover 1000 operations, MIRES needs about 45 seconds, that is the sum of the locking phase and the reconstruction phase times. However, as the database is only locked in the locking phase, in the case of recovering 1000 operations from the 45 seconds required to recover the application is only inoperable for 15 seconds, which means an increase of 30 seconds on the availability. This test aimed to check how long it takes to reconstruct a document through the execution of operations. We concluded that there is a significant increase in the reconstruction time with the increase in the number of versions of the document. For example, it takes between 0.1 to 0.2 seconds to reconstruct a document with 100 versions, while it takes between 2 to 3 seconds to reconstruct a document with 10,000 versions. However, if we use snapshots during the reconstruction of the document, we could decrease the reconstruction time by using snapshots to mitigate the necessity of execute all the operations related with the document. With this work, we are able to conclude that Backend-as-a-Service is a viable way to develop applications, but the existence of vulnerabilities can compromise its state and normal functioning. And in that context, we introduced MIRES, an intrusion recovery service for mobile applications supported by Backend-as-a-Service. We also saw that since there is no focus on mobile applications in past works, MIRES is the first one related to the area, introducing a set of new approaches and solutions such as the two-phase recovery and the user's recovery mechanism. Once again, thank you very much for your presence, and I hope that you have enjoyed this presentation.
Hello, my name is Igor Zavalishin. I will be presenting the paper called My House, My Rules, a private by design smart home platform. This is a joint work with my supervisors, Nuno Santos, Ramin Sadra and Axel Legay. So to give you some context about what I'm going to talk about, let's define what smart home platform is. So smart home platform provides a single point of control for all the devices that you have in your smart home. It offers a seamless device setup, so making it much more easier for you to install and add new devices. And it provides hundreds of third-party applications that you can use to control your devices and to create automations. There are quite a lot of those platforms nowadays. There is Alexa from Amazon, there is SmartThings from Samsung, there is HomeKit from Apple, there is Google Nest. While there is a variety of those platforms, they all employ the same approach, which I call ABCD. Always be collecting data. What it means is that all the device data and user actions is aggregated and processed inside of the remote cloud storage provided by the platform provider. And this usually is outside of the reach of the user, who is the owner of the devices and their generated data. This creates an obvious privacy problem because the user usually has no way to verify how that device data and user actions is actually used by the platform provider and who it is shared with. And this creates a privacy risk, which was confirmed by numerous news headers like accidental data leaks, massive data leaks due to security problems, unauthorized data sharing with law enforcement, and in general the platforms were found to be insecure and vulnerable to various attacks. Previously, a lot of researchers have proposed solutions to improve the privacy and security properties of these platforms, and here I list just several of them. A common problem across all those solutions is that their threat model considers only malicious application developers, but considers the platform provider itself to be trusted. We believe that both those parties are equally worrying and dangerous in terms of user privacy and should be addressed together. And that is exactly what we are trying to achieve with the system we propose. We named our system Patriot. It provides a private by design IoT platform in which users retain full control over the device data and can enforce their privacy and security preferences over the data sharing and processing capabilities of the installed applications. The applications must strictly follow those rules, otherwise they will be blocked. So let's go through the overview of the proposed system. Here is a high-level structure of the platform and how it is being deployed. We see on the right, in a smart home, there are devices that are connecting to the Patriot service running inside of the cloud infrastructure. And its central component is TSAR, which is short for Trusted Smart App Runtime. It manages the state of all the devices and hosts all the applications that are installed by the user through the management mobile app and grabbed from the application storage. The whole Patriot software stack runs inside a memory-isolated environment provided by Intel SGX. And in this case, the environment is completely secure from untrusted operating system running in the same cloud environment, and even physical access by the admin of the cloud provider. We envision the Patriot is open source and provided as a Docker image to anyone interested in, that the users can deploy them freely on their own personal servers or on the public cloud providers such as Microsoft Azure Confidential Computing that provide SGX support. Now, Patriot provides a way for application developers to build their applications using a novel element-based programming model. Why did we need a new programming model? This is usually actually quite important to explain. Existing smart home platforms often rely on permission-based access control, which proved to be useless in protecting user privacy. Why? Because most of the time it allows the users to control the devices that the application can interact with, but not the data processing and sharing capabilities of those applications. This usually results in a situation when the application, when it was granted access to a specific device, can freely share the data that it has access to. Because network communications in some of the platforms are completely unrestricted for the applications. So what we can do with that is to make some mechanisms that will make internal data flows inside of those applications explicit and verifiable, so that the users could understand what the application is actually doing with the device data that it has access to. So how we are going to do that? We propose to represent all the elements as a graph of elements. We propose to represent all the applications as a graph of elements. So to illustrate this concept, let's consider the Watch My House application. What it does, it grabs images from the IP camera and forward them to the cloud storage, for instance, Dropbox of the user, for backup. And the logic of this application can be broken into three main features. The first one will be grabbing the frames from the IP camera, and this can be represented by the IP camera element, which implements this functionality. Then the second element will be preparing a payload for the HTTP request to the Dropbox service. And the final element, which will be doing actually HTTP request to that service. So as you can see, we can represent the whole logic of application by using just three elements connected together. In this case, the edges between the graph nodes, which are represented as elements, show the only path of the data flows inside of that application. We can clearly see two data flows, one from IP camera to Watch My House element carrying the image data type, and the second data flow from Watch My House element to HTTP request carrying the same image but as part of the request. Some of these elements are provided by Patriot API. In this case, they're marked with white background. It's IP camera and HTTP request. And other elements can be provided by the application developer because they will implement a specific application logic. In this case, that's Watch My House element. And for this specific application, the application package will consist of the graph description, which it can be textual and describes just types of the elements the application depends on and their respective connections, and also the code, which in our case is JavaScript code for the app-specific elements, in this case Watch My House. Now, Patriot provides a rich library of built-in API elements that application developers can use in their applications. They range from the elements responsible for interfacing with devices like cameras, lights, or various sensors. Other elements can perform network calls, like the one we just saw. And other elements can help you to process the sensor data, for instance, run object detection or run speech recognition. There are also elements that allow to start applications at a specific time of the day or week, based on the schedules, and others. Another cool feature of that element-based approach is that some simple applications can be implemented without even writing a single line of code by just combining existing built-in elements together. And we illustrate this concept with this simple app called Light My Path, which turns on the lights depending on the motion being detected and turns it off after a certain time. As you can see, there are no elements that were provided by the application developer. The application itself consists of three built-in API elements. Now, the users have to have a way to specify their privacy preferences, and those privacy preferences has to be enforced on all the data flows generated by the applications. And we think about the privacy policy as a set of rules that define all the potential data flow that can take place in a smart home. And we ask the user to define those and think about those as per device or device type data flows, instead of thinking about what data flows can be generated by each specific app. This makes it easier for the users to reason about potential privacy-sensitive flows in his or her smart home. And the rules are defined in a format that is quite straightforward. You have a source of data, you have a sink where the data flows, and you have to specify the type of data of that data flow. And the rule can allow a specific data flow or block it, depending on the condition. And users can also specify specific time restrictions and exceptions for data flows. Now, Patriot provides a specific design of the UI that will help the user to specify the privacy policy for the devices he has. And the UI actually guides the user along this process. So first the user decides what the rule type, whether it's allow or block type. Then he selects the specific source of the data flow. In this case, it's a living room camera. Then he has to specify the type of data from that specific source, which in this case is video. And then the sink where the data has to flow. In this case, a Dropbox service. Optionally, the user also specifies the time restriction and the day. Now, in order to understand whether the application that the user installs actually complies with the policy we just specifies, Patriot has a specific security monitor called Flowwall that implements internally the policy evaluation algorithm. The algorithm itself works as follows. It grabs all the application graphs that are installed in the system and models those graphs with Prolog. And based on that model of the application graphs, it creates a data flow matrix, which combines all the potential data flows generated by these installed applications. And then, based on the policy rules that are specified by the user, it creates a policy matrix, which later on is used to match against the data flow matrix to determine the execution state of all the applications. If any of the data flows in any of the application violates any of the policy rules, it will be blocked. Otherwise, the application is allowed to be executed. The state of all the application is inserted in the so-called action vector that defines the execution state of all the applications. Now, we'll describe the implementation details. Patriot was implemented in JavaScript. It runs on top of Node.js with V8 engine. The UI for the users to interact with Patriot was based on React. We rely on Scone libraries to execute Patriot inside SGX enclave. And we use Scone's remote attestation at startup to attest the integrity and authenticity of the Patriot core files. And we distribute Patriot software stack as a Docker image. Here is an overview of the software stack of Patriot. As you can see, we have elements of the Watch My House application here that communicates through event bus, and with they also communicate with device drivers. Here we have a runtime manager that decides that initializes the elements of the applications and sets them up, and the Flowwall security monitor that determines the state of the application depending on whether they comply with the privacy policy of the user. Down here we have cross-compiled Node.js binary, cross-compiled across against the Scone library, and it also has a built-in Prolog engine that we also cross-compiled across with Scone library. And all of these runs inside SGX enclave. Down here we have in the file system of the Docker container, we have the application package files as well as user-defined policy and configs. This is how the UI for the user to specify policy rules looks like. And now we will describe the evaluation results we've got. So we evaluate Patriot on three fronts. First, we analyze the performance of it and evaluated the overhead that SGX introduces. Then we evaluated the expressiveness of the policy, how efficient it is in terms of defining the expectations of the users. And finally, we evaluated the usability of Patriot. For this evaluation, we set up the case study with that emulates a real smart home scenario with 10 devices deployed in it, ranging from cameras to voice assistants. And we developed 20 Patriot apps that made sense for this specific scenario. For the testbed, we used two powerful machines with Ubuntu installed on it, with latest version on Docker and latest security patch and driver of SGX. In terms of performance, we first evaluated system initialization time and compared while running Patriot inside SGX and outside of it. The biggest time was taken by the attestation, and usually most of this time is taken by communicating with SCOM's configuration attestation service, which was running on the other machine in this case, and also decrypting the call files of Patriot. We sealed the file system of the Docker container of Patriot and encrypted completely, and decrypted only after successful attestation with a CAS server, with which we can guarantee the integrity protection of the Patriot core. Here we see that the bootstrap time is not significantly affected by the SGX overhead, and the only significant difference we see in the app loading time. This is due to the fact that the application package is encrypted and has to be decrypted inside the SGX whenever the application is installed. Usually it takes some time inside SGX. Now, we also performed a load test to determine the maximum throughput the applications, the Patriot can support, as well as compared to the Apache server running on the same platform. So we see that we observe 5 times decrease in the throughput when running Patriot inside SGX, which is significant. And this is mostly due to the fact that we rely on SCOM library, which is not optimized for network-intensive applications like Patriot. In the future, we might consider switching to another library OS to deploy Patriot inside SGX. Now, in terms of application performance, we see no significant differences when running applications inside SGX or outside of it. The average runtime difference is 13 milliseconds. We see difference in the amount of time taken by the Prolog engine to model the application graph and extract the data flows. But still, the Prolog query takes on average less than 5 milliseconds, with few exceptions. When the application graph is quite big, it takes a significant amount of time, but still within 70 milliseconds. Now, to evaluate the policy expressiveness, we defined few policy rules that made sense for our use case scenario, and we checked how those rules will affect the performance of the applications. And we observed that most of the application continued to operate nominally, even with these rules being activated. This is due to the fact that most of the applications rely on device-to-device data flows, which are usually unaffected. And if some of the applications are blocked by the specific policy rules, users are always able to specify custom rules that will allow specific data flows for certain device types or devices. Now, for the user study, we had 45 participants, mostly from our department, and the whole user study had 2 stages. In one stage, we were asking for privacy preferences with regards to the case study scenario that we had. We wanted to know what users think and how users think in terms of device data flows. And in the second stage of the user study, we were having some practical task for the participants. They had to specify a certain policy rule, install and verify the application. So in terms of privacy preferences, we observed that most of the users are concerned with the data flow that span across several domains, mainly those that flow to internet. And they are less concerned with the device-to-device flows. And this is in line with our expectations and previous study results, so that was in line. In terms of user experience, we were happy to know that majority of participants found Patriot to be easy to use, and that is quite important result, because most of the privacy-oriented solutions nowadays require significant knowledge from the users to operate, and that end up usually with people ignoring the privacy protection that those solutions offer. In this case, we see that it's quite easy for users to use Patriot, so we hope it will be helpful for them. Now, I want to finish with a few takeaway points. We just described Patriot, which provides a private by design platform for smart home users. It implements an element-based programming model which aims to make data flow inside applications explicit and open to verification. It provides a fine-grained over the data flow for the users who install the applications and use Patriot, and it provides a mechanism for those users to enforce their privacy preferences. I'm happy to announce that Patriot is open source and you can always use it in your own projects or in research projects. Thank you.
Hi everyone, I am Mohammad Ariful Alam. I'm an assistant professor in computer science in the University of Massachusetts Lowell. I'm presenting a paper, this AI Fairness Towards Activity Recognition of Older Adults. Here's my outline of my presentation. I'll introduce the problem, then biases and disability, then bias existence in activity recognition of older adults. Then I'll define how we detected the biases and mitigated the biases to confirm AI fairness. Finally, I will conclude my presentation. So, machine learning in healthcare fairness is a really latest concern. There is an article published in 2019 in October that New York regulator probes United Health algorithm for racial biases. The problem is the United Health predicts future healthcare cost of patients using machine learning, and that provided that the white people, they are getting higher future cost than the black people. And based on the future spendings, intention of future spendings, they are trying to provide the emergency service. So the problem is the algorithm is designed to predict whether a person needs to be admitted in emergency or not. But instead of defining whether the person is in need or not, somehow internally it's calculating the future healthcare cost intention. And apparently the black people are getting neglected and they are not getting admitted in emergency facilities as predicted by the algorithm. So this concern raises huge issue in the healthcare fairness. And the problem is not with the human, or not with the not with the people who annotated the data. The problem is with the algorithm itself. So let's take a look how this data has been collected. So the medical practitioners, they ask questions and take histories. Then they ask whether you would like to be admitted or not, given the cost, or not given the cost involved in insurance coverage. So higher health cost makes some people decide not to get admitted due to their financial condition or insurance coverage. Who decides not to go with emergency care due to cost? Most of them are turned out to be black. So if not get admitted considers as low risk, and black people are being predicted with low risk for emergency healthcare needs. That's the problem with this entire data collection. And once the data has been collected, the machine learning model learns that and predict the racial bias. So the racial bias or any kind of bias can be happen for different reasons, like the skewed sample, tainted examples, like the sample size disparity, limited risk features, even the proxy data implicitly encoding sensitive attributes. So the bias is also really significant in disabled people. Like my former colleague Sherry Truin proposed a study like the AI fairness of people with disabilities. She mentioned that disability is not a simple variable like the other predicted variables such as age, race, and gender. The greatest difference is the diverse nuances and dynamic nature of disability itself. So disability is not a simple variable with a small number of discrete values like the age, race, or gender. It is totally different. It has many dimensions. People can experience multiple disabilities, and over the time, the disabilities could be also different. And this impairment and health conditions that can lead to disabilities are not only diverse, but vary in intensity and impact, often change over time. So that exactly we are going to talk about here. One paper published in recently, this is one of my major contribution of my PhD work. We collected 22 persons' data, all are older adults from different ranges of ages. And the gender diversity in the recruited reflected the gender distribution of the facility. So that's actually fair. We confirmed that it follows the exactly same ratios. And a trained gerontologist evaluated complete surveys on participants to fill out the surveys. And we collected huge data, variables, and ambient data, and 13 different complex activities we collected. And we have the wearable sensor of accelerometer in their hand. And we have, once we collected this data, scripted data, we found no diversity in activities because we instructed them to perform the activities. And once we collected some unscripted activities like that, we asked them to do whatever they want for 2 hours, and we figured it out there's some diversity. Like we found that the activity has been diverse specifically for walking. Like the older adults, they may walk normally. Sometimes they take stick, mostly on the climbing stairs or some for no reason, or getting up from the chair. Sometimes they use walker, and that's the problem. So in the training data set, we did not have those information, but in testing or the unscripted data, we have. So we applied activity recognition model, like the hand gesture recognition model. We built a eight different hand gesture category dictionary, and we applied several signal processing, and we extracted features to get the hand gesture. And using the detected hand gesture, we use a signal separation model, is a sports deconvolution model to separate out the signals from the hand gesture related signal. This is like kind of like this, like that we have the originally these dotted lines are original x-axis of the accelerometer. Then we have the reference. This reference has been generated from the previous learning, and we extracted some approximately sparse signal. That signal represents the person's postural activity. So this is relevant to the postural activity, and the upper one is relevant to the hand gesture activity. So we use this to train another model, like a support vector machine model, and got some activity. So we have the two signals. One is for gestural level activity relevant signals, another is postural level activity related signal. So both of the signals we pass through a deep learning model. The deep learning model is a multitask, multi-level deep learning model. So here you can see that the postural, the gestural and postural level signals that we extracted from the deconvolution, and several LSTM model layers been parsed, and finally we have the gesture level. And using the gesture level, we the soft selection model, and we predict the posture task as well, the posture level. So using this multitask, multi-level activity recognition model, we can get gesture level activities and posture level activities. Then we got some accuracies here. this is the gesture activities, and you can take a look there from our previous method. This is our previous method published in PERCOM 2017, and we can figure it out that the activity recognition is really high in different gestures, hand gestures. And posture level activities, if you consider only 4 activities, you can take a look there. Our new model, like the recurrent neural network, can provide also higher accuracy. The problem is here, when we consider not 4 class, now we consider on the unscripted data, and we consider 6 class, you can take a look there. There's some things wrong with there. This activity and this activity, where only temporarily disabled people use those follow this pattern. So these particular activities are really low than the other activity recognition accuracy. And this is actually disability bias. So we go for further investigation, and we can take a look there. We did several trial and errors, and we figured it out. The bias is really high when we consider the privileged group of age less than 80, and they have really high accuracy of walking detection than the age greater than 80. You can take a look there. When the person is using walker, the accuracy drops really high, 6%. And when person is using stick, and also accuracy drops 5% less than their 80 years less than people's comparison to that. And when we consider the ability, like the whether a person is able or disabled, like the functionally able or functionally disabled, we can also see that there's some discrimination of the accuracy performances as well. So here you can take a look there. The functionally able persons, the machine learning model is able to identify their walking activity really well than if the person is disabled. And similar for the walking stick, you can take a look there. When a person is walking a stick, the disabled person is providing really low accuracy. And this is also similar. This is also high for even 4-class problem as well. And we also collected a few more data, like the anxiety level, depression level, and dementia level. And if we did not figure it out, we could not find that much discrimination. But for this, like the functional ability and the age, it's really providing discriminatory accuracy out here. So we investigated several, and we implemented several bias detection methods first. So we used the first method we used is statistical disparity, that computed as the difference of the rate of favorable outcomes received by the unprivileged group to the privileged group. The absolute matrix is 0, but it never can be achieved in real life. So the matrix fairness is between -0.1 to 0.1. If this statistical parity difference is between this range, that means the algorithm is fair. We implemented another bias detection method, that is equal opportunity differences. This equal opportunity difference provides the equal opportunity of each of the privileged and unprivileged group, and it is a probabilistic difference of the opportunities. And when it is also similar to like between -0.1 to 0.1, then we consider it as fair. And we also implemented several other methods, like the average R differences. It is also range the same. Then we included like the disparate impacts. That the fairness matrix, the impact probabilistic, the impact disparate impact disparity would be range from 0.8 to 1.25. In that case, we'll consider that as fair. Then Thiel index, that we consider at the same range of -0.1 to 0.1. Then we implemented also some debiasing techniques, like that we use the data reweighting technique. Then we use the adversarial debiasing. This is one of the most popular debiasing technique in the world currently. where we considered like the privileged group of age greater than age, the privileged group age less than 80, and unprivileged group age greater than 80, and privileged group would be able, and disabled would be the unprivileged group. So we also implemented several advanced debiasing techniques, the rejection option-based classification, equal odds, disparate impact remover, then learning fair representation, calibrated equalized odds, and prejudice remover. So we implemented all of the methods like the bias detection and bias mitigation, debiasing technique in Python framework. So the idea is we have a lot of bias detection technique and we have a lot of bias mitigation technique. How you're going to come up with a conclusion that the current condition, the current model is debiased and we detected that, and which method is best for debiasing? That's really difficult. So we considered a strategy, like we consider all of the methods, and that will be like this. So suppose we have 4 fairness metrics and 8 debiasing technique. So among these 4 different fairness metrics, how many of them providing fair, unfair? And this fairness, the unfair providing before debiasing and after debiasing. And we'll keep monitoring the accuracy drop as well. So the most fair, according to all of the 4 fairness metrics, with lowest accuracy drop would be the best debiasing technique selected for this method. So we run that, all of the 8 different different debiasing technique, and you can take a look there. This is the we can take a look there. This is the statistical parity differences and disparate impact, average odds differences, and equal opportunity difference. Several detection technique we applied here, and based on the detection techniques, we figured out there, like the statistical parity difference metrics out here. You can take a look there. And we found that before applying any kind of debiasing technique, you can see that the fair matrix is between this one. So we can find that there is a 0 fairness available here. That means this is totally unfair. This model is totally unfair. And here you can take a look there from 0.8 to 1.25 disparate impact. We found only 2 detection. That means it's 2. And after applying the debiasing technique, we figured it out that we need to be fair in between in this portion, and we can see that only 2 of them detected fair, and so on. And similarly and we did that for the privileged group less than 80 and privileged group of able. And we can see that there's some changes of the fairness after applying different debiasing technique. And this is not clear about this diagram, but we can chart it out this way. So the accuracy drop, we need to minimize the accuracy drop and also maximize the fairness. And you can take a look there. There are different the debiasing technique provides different accuracy drop and different fairness. We can see that this method is totally fair because all 4 detection method provides it's fair, and also here. But we figured out that this has higher accuracy drop than this one. So for age group debiasing, if we consider the age group debiasing, then we need to select the rejection option of the debiasing technique. And on the other hand, we figured out that this is we've found a fair bias here, debiasing technique here, and also fair debiasing technique here. That's the maximum fairness. But we figured out the disparate impact remover. This particular debiasing technique provides us less accuracy drop, like the 2.5, with highest possible fairness. So We investigate. This paper is actually an investigation paper. We investigated AI fairness in activity recognition, and we apply a debiasing method selection strategies. How we're going to select debiasing technique given few bias detection methods based on the accuracy drop tolerances. A similar method can be applied with any domain. That's it for my presentation. Thank you so much.
Hello everyone, my name is Bakit Al-Judani and I am from the Center for Research on Engineering Software Technologies Research Group at the University of Adelaide, Australia. I will be presenting our work, Security Awareness of End Users of Mobile Health Applications, an empirical study. This work is a part of my PhD research and it's co-authored by Akash Ahmed, Mansoura Zahidi, and Muhammad Ali Babar. Here's the outline of my presentation. I will introduce the topic through a brief background and motivations. Then I will highlight the research objectives and walk you through the adopted research method. After that, I will present the findings and threats to validity. Finally, I'm going to conclude the presentation and throw out some ideas for extending this research. So, as we all know that we currently live in a digital technology era and many things have become smart, including mobile phones. Mobile phones have become an inseparable part of our daily lives and we carry them everywhere in our pockets. In 2019, 5.2 billion people, that is nearly 67% of the global population, subscribe to mobile services, with an expected increase to 70% by 2025. Mobile phones are considered unattractive for many reasons. First, portability, computational capabilities, context sensitivity, enhanced interactivity, user-friendly interface, etc. Mobile health apps, or mHealth for short, are on the rise with 350,000 apps available in the major app stores, that is Android and Apple Store. The market revenue for digital health expected to reach $31 billion by 2020. mHealth apps have the ability to connect mobile technologies and health industry to provide a variety of low-cost, efficient, and digitized health services. As we can see here on the right, mobile health apps can be categorized as general health apps such as patient management apps, clinical apps, and fitness monitoring apps such as activity tracking and nutrition apps. Despite the offered benefits of general health apps, security of health critical data remains a challenge. Compromising health critical data would lead to social, legal, and financial consequences. Now I will explain the role of end users and why we consider end user security awareness as an important research to investigate. mHealth apps on the one hand, mHealth apps developer on the one hand strive to ensure and deliver secure apps. Yet, technical solutions cannot address security alone. On the other hand, end users' understanding of security issues is essential to ensure secure mHealth app usage. End users find security which have been developed by the developers are hard to understand. As a result, end users can be misled by app permissions to disclose their health data, or end users can get deceived by hackers to leak their private information. So here's an overview of the methodology that we adopted. We have done a literature review to understand what studies have been done so far and what are the missing gaps. So based on that literature, we specify the research questions for this study, which are: the first research question is, what is the level of security knowledge, attitude, and behavior of end users about using mHealth apps? And the objective is to measure the level of knowledge, attitude, and behavior. We use descriptive analysis to report and answer these research questions. And the second research question is, what are the relationships between security knowledge, attitude, and behavior? And how do they influence end users while utilizing mHealth apps? So to find answers, the objective of this question is to analyze the relationship between knowledge, attitude, and behavior. And we used linear regression tests to find answers for this question. In addition, literature review allowed us to identify the security mechanisms and security critical scenarios that end users are concerned about. So we identified 4 main security mechanisms, namely privacy, access control, encryption, and authentication. And we identified 8 security critical scenarios, as we can see here. The literature also helped us to identify the data collection method. So we used human aspect of information security questionnaires. More specifically, we use CAB model, knowledge, attitude, and behavior model. So to define these 3 terminologies, here, security knowledge refers to what end users already know. Security attitude refers to how end users feel about that knowledge. And finally, security behavior refers to what actions end users perform to ensure security. And here is an example of a CAB model. For each of the 8 critical scenarios here, we identified 3 statements, one related to knowledge, one related to attitude, and last one related to the behavior. And here's the example. So we ended up with 23 statements. We excluded 1 statement because it was not actionable. and the given responses were true, false, or I don't know. The second research phase is outline the research hypothesis. So we outline 3 hypotheses. First hypothesis is security knowledge of the end users of mHealth apps has a positive correlation with their attitude. Hypothesis 2, attitude of the end users of mHealth apps is positively correlated with their behavior. And lastly, security knowledge for the end users of mHealth apps has a positive correlation with their behavior. The third step is collecting end user responses. So we collected data from 2 health providers in Saudi Arabia. Those health providers were purposefully selected because they provide mobile health apps for their patients. These apps contains health critical data such as medical history, lab results, radiology test results, etc. First, we conducted a pilot survey with 10 end users, that is 10% of our respondents, to find out any ambiguity. And then we collected 101 responses. And here on the left, a snap of our demography information of our respondent. Interest reader can refer to the paper for more details. Last step, we perform data analysis. So since most of our data is quantitative, we used SPSS to help us report our results. So descriptive analysis was used for end users demography. We used Combac Alpha for understanding the internal consistency. We used Pearson bivariate to understand the correlations. And finally, we used linear regression test to understand the proposed hypothesis. So before going to the actual results, we wanted to measure the internal consistency of our survey statements. So we calculated the Cronbach alpha. The obtained results, as we can see here from the table, have met the minimum acceptable coefficient values, which is greater or equal than 0.7. Second, we conducted a Pearson correlation to test the strength and association direction between the survey statement. We found that all the survey statements showed a positive relationship ranging from strong to a very weak, except 2 statements had a very weak negative relationships. 61% of the survey statements had a significant relationship. To answer research question 1, which investigate the security knowledge, attitude, and behavior of end users about using mHealth apps, we use descriptive analysis, including means and standard deviation to find an answer. So end users have different opinion about the surveyed security issues, knowledge, attitude, and behavior. For one security mechanism, knowledge and attitude were contradicted. As an example of such a variance, 2 encryption-related statements provided to examine respondent knowledge and attitude toward applying encryption within the used mHealth apps. We found that 42% selected true for the knowledge statement and 46% selected do not know for the attitude statements. For answering research question 2, which is testing the first hypothesis, we use sample regression tests to understand if security knowledge influenced the respondent attitude. We found that knowledge had a statistically significant impact on the attitude, producing R-squared 1.602. This means that respondent knowledge accounted for 60% of the variance on their attitude. And hence, respondent knowledge is positively related to their attitude. To further answer research question 2 and find answer for the proposed hypothesis, we use multiple regression tests because we have 2 dependent variables this time. So we found that both knowledge and attitude have a statistically significant impact on behavior, producing R-squared to 0.526. Respondent knowledge and attitude account for 52% of the variance on their behavior. Coefficient values resulted from the test indicated that attitude predictor is statistically significant. However, knowledge predictor is not statistically significant. So the key findings are respondents have different level and opinion about the survey's security issues. Such differences are mainly depending on different factors such as educational backgrounds, period experiences, etc. And based on the regression test, relationships results imply that we accept H1, knowledge is positively correlated with the attitude. Accepting H2, attitude is positively correlated with their behavior. Rejecting H3, security knowledge for the end user of mHealth apps has a positive correlation with their behavior. For threats to validity, we believe that our study might get affected by the self-reported behavior for our respondent. Also, the source of data collection, which is limited to 2 health providers in Saudi Arabia, and the size, 101 respondent, which can affect the generalization of the study. Finally, policies, regulation, and practices to be followed by health provider might affect our study. For our conclusion, we found that knowledge strongly influences respondent attitude towards security of mHealth apps. Knowledge does not significantly influence respondent security behavior. Out of that, we draw up some recommendations. First, security training of end users, threat analysis workshops need to be ensured by mHealth providers. There is a need to promote best practices to enforce security, such as multi-step authentication. And it is important to adopt suitable mHealth apps, trade-off between security and usability. For future work, we believe that this work can be extending through collecting more data with different health providers and end users at a global scale. We also believe that this study can be measured the security awareness beyond mHealth apps, such as social apps and mobile banking apps. And we believe that it can be extended by measuring the security awareness via simulation-based attacks. We acknowledge the Research Center at King Fahd Medical City and Dr. Suleiman Al Habib Medical Group for approving our study. We acknowledge all the participants who involved in this study. We also acknowledge the support of CRUST team members. Thank you. Any questions? Please feel free to email me at this email address. Thanks.
Hello everyone, I'm Mohammad Ariful Alam from University of Massachusetts Lowell. I'm presenting a paper that's called AutoCogniSys, an IoT-assisted context-aware automated cognitive health assessment system. So here's the outline. I'm going to talk about some introduction-related works, overall architecture, some activity recognition, activity feature estimation, physiological signal processing, experimental evaluation, conclusion. So the Alzheimer's, approximately 5.2 million people of 65 and older adults are suffered with any form of cognitive impairments in the United States as per in 2012 statistics. So dementia is one of the major causes of them, and cost of dementia is also really high. And you can take a look at the cost in 2016. It was about 15 million paid cost and 18 billion hours on paid assistance, and and in total payment to the nursing facility is 230 billion, and this number would be 1.1 trillion in 2050. So the Alzheimer's assistance is really expensive. So wearable sensors can help. So because it can capture the number of steps, the physical activities, sleep patterns, and physiological outcomes of older adults. So ambient sensors also help capture the movements patterns of objects. So researchers also proved that the existence of correlation between cognitive impairment, everyday task performance, as well as physiological symptoms. So a lot of opportunities to accommodate proper assistance to Alzheimer's patients or dementia patients using the Internet of Things or wearable and ambient sensors. So there's some challenges out there in building such a assistance system, or you can consider like the health assessment system. So we need to do continuously health assessments using the IoT system. The problem is we need a real-time multimodal IoT system. And to confirm higher accuracy, we need multimodal context fusion. So in this paper, we focused on the challenges and we built a cognitive health automation system where we combined ambient sensors and wearable sensors. The ambient sensors are all motion sensor, object sensor, and several other things. And wearable sensors, mostly accelerometer sensor, electrodermal activity or galvanic skin response, and photoplethysmography that's helpful for heart rate detection. So we used all the sensors like the accelerometer sensor in the wearable watch and ambient sensors to detect complex activities. Then we used some noise elimination technique to remove noises from accelerometer, electrodermal activity, and PPG sensors. And finally, we implement and evaluate our entire system from real world collected data from the older adults. So there are some related works like the Smart Faber, proposed non-intrusive sensor network-based continuous health smart home environmental sensor acquisition, and a novel hybrid statistical and knowledge-based techniques to analyze the data to estimate behavioral anomalies for early detection of mild cognitive impairment. It's more likely unsupervised, and it considers the anomalies. And also, like the Skubik, he also presented an example of unobtrusive continuous monitoring system for purpose of assessing early health changes to alert caregivers about the potential signs of health hazards. This is a recommender system rather than it is health assessment. Also, we showed previously that the correlation between the physiological sensors and physical sensors along with the dementia status, 2016. So our overall architecture like this, we have a ground truth collection system, we build the smart home environment, then we collected data and we recognize activities, complex activity recognition in hierarchical pattern. Then we extracted several features like the activity features, electrodermal activity features, PPG features. Then we combine all together to recognize cognitive health. That means whether a person has no dementia, mild cognitive impairment, or total dementia. So we first developed the smart home. The smart home looks like this is a pogo plug smart computer. It is connected wirelessly with, it's a Wi-Fi signal connected with 3 binary passive sensors, 2 binary object sensors, 3 IP cameras we attached at the beginning, but for the overnight data collection, we removed the IP camera. Then 1 input wearable watch. It's called Empathic A4. That has been used for, there's a PPG sensor, EDS sensor, and body temperature sensor, and accelerometer sensor has been out there. So we recruited 22 participants, and the gender diversity maintained exactly to the facility. And a trained gerontology graduate student evaluator complete surveys with participants to fill out several surveys. And each of the surveys provides different information that I'm going to talk about in a while. So the participants are given wristband to wear on the dominant hand, and concurrently another trained IT graduate student have the IoT system set up in the participants' own living environment. So the participants are instructed to perform 13 different complex activities, and another project member remotely monitors the entire data collection. The entire session lasts 2 to 4 hours time. So we collected few demographic data. First one is the observation-based St. Louis University mental status that can provide us no dementia, no cognitively impaired, mild cognitively impaired, and cognitively impaired estimation. And we have observation-based activity feature extraction method that can provide us the completeness of task, sequential task ability, and avoidance compatibility, like the interruption avoidance compatibility. And we also collected several surveys like the Yale Physical Activity Survey, Latin Instrumental Activity of Daily Living Survey, Bartle Index of Activities of Daily Living, Geriatric Depression Rating Scale, and Zong Scale for anxiety level. So at the very first challenge we did, the automatic health assessments for older adults, that is automatic activity features assessments. As our gerontology experts detected like the task completeness, sequentiability, and interruptions, and total task scores manually, we want to predict that automatically using the IoT sensors we have. So the first step is to recognize the activities, and then we want to extract these activity features like that. We want to estimate these activity features based on supervised and unsupervised method. And the second type of health assessment is the mental health assessments. This one is the physical health. This is the mental health assessments for older adults. This is cognitively impaired, mild dementia, or complete dementia. So in the steps, we followed the PPG signal extraction, EDA feature extraction, and context-aware automatic health assessments. So this context that has been detected here, that should be aware of here to detect the mental status. So the complex activity recognition, we did not propose something new. We borrowed some idea from our previous model that we proposed. We actually used the sparse deconvolution method to separate out the hand gesture and postural activity signal. Then we applied support vector machine to recognize postural and gestural activities altogether. So we have the gesture activity, posture activity, we have ambient sensor information and object sensor information. So we consider this as a 4-tuple of our problem, our complex activity recognition problem. Then we used our previously proposed hierarchical dynamic Bayesian network model. In previously proposed model, we had only the posture and ambient sensors. And now we have the gesture, posture, ambient, and object sensor all together. So we applied that model on 13 scripted activities we collected. So 13 scripted activities data we collected that has automatic activity features estimation. We use that. So to detect the feature, like the feature activity features, that means the functional ability of performing activities. We use observation-based method that decides the task completeness, sequentiability, and interruptibility. The final task score is the summation of all three. So the idea is we define each of the 13 activities. These are all 13 activities, like the telephone calling, receiving, and other things. We define each of the activity as a sequence of sub-activities or subtasks. When the sequence break, we have the task sequence penalties. When the one sequence is not complete, we have the task completeness penalties. And when someone has started something and interrupted with another from the later sequence, we put penalties of interruptions, and the total score would be the task score. In this way, the nurses, they evaluate the observation-based activity features or activity ability. So we developed 4 supervised algorithm that a support vector machine algorithm to predict 3 tasks and 1 total score. And in this, all of the algorithm has these common features and different labels. These labels are from the expert nurse provided evaluated labels, and we trained that one. So we used also we used unsupervised method of dimensional reduction as well, along with the supervised method, and this dimensional reduction provides us a single score that we consider as a task score as well. So for automating mental health assessments, let's talk about what is mental health. So when we talk about mental health, we talk about the autonomous nervous system in our brain. So when someone is getting stressed, that person's get autonomous nervous system activated, and this system activation can provide some skin conductance or skin conductance improvement, and also the blood pressure and heart rate beat changes. And that changes can be captured using the electrodermal activity that can provide the skin conductance, and also PPG or photoplethysmography that can provide the instant heart rate. So the EDA signals look like, the ROID signals look like the dotted lines here. So the problem is this EDA signal is really erroneous. It is a combination of cognitive, several arousals, like the cognitive arousals, affective arousal, and physical arousals. So we only need this cognitive arousal. So that's why we applied several noise reduction technique. This is a steep rising noises reduction technique that we followed here. And also you use the convex optimization technique to apply deconvolution on EDA signal and extract EDA features. For PPG sensor signal processing, you can take a look there. The PPG signal is also erroneous. So we use the periodic moving average filter, and we detected the heart rate variability from PPG signal and also the heart rate. And finally, we extracted several features that are relevant to the heart rate variability. So here is just some of the features like that. These are the PPG signal features, and these are These are actually EDA signal features. And these are the heart rate variability features. We have 1, 2, 3, 4, 5, 6, 8 features here, and 7 features here, and 8 features here. So in total, we have 15 features. So we provided the activity recognition accuracy. You can provide our overall model is better than several other models. And also the postural and complex activity recognition, they are also outperforming our used model here. So also we did some correlation analysis where you can take a look there. The interactions, particularly interactions, has high correlation with cognitive impairment, like the not cognitive impaired, mild cognitive impaired, and cognitive impaired. And also sequentiality has high correlation as well. And we applied the supervised method that we developed before, and we figured it out that the supervised model detected activity has also high correlation with the cognitive impairment, and also sequentiality also has high correlation here. And we used unsupervised method, and we figured out that unsupervised method has high correlation with cognitive impairment as well. So on the scripted activity features, we apply all of the 7 features of EDA and 8 features of HRV, and we apply the partial correlation analysis, and we figured out that we have not a good pattern of the correlation of EDA and HRV. So we found correlation here and high correlation here. This does not make much sense. So I'm gonna talk about how to make it sense. So we use the support vector machine algorithm, and we use a baseline algorithm as well. And then we figured out that if we use only interaction score to train the support vector machine, and we found that to detect the cognitive ability detection is almost 72%. And if we use only sequence activity score, that is the detected, like the algorithm produced sequence activity score, that's all close to 70%. And unsupervised method produced task score based cognitive ability prediction also provides some accuracy, but if we combine all together, all the things like the interaction sequence, unsupervised activities, and activity score, EDA signal, and hidden and HRV signal, everything all together, we can see that detecting of cognitive ability of the person is almost 92%. And we also consider that what's the impact of each of the activity. That means which activity is enough for us to monitor over the day to detect the person's cognitive ability. And we figured it out that here you can take a look there. The door opening, surprisingly, the door opening event is providing high accuracy if we consider only the EDA signal. And other than that, we can figure it out that the trash out is also important, and also the making phone call is also important. When a person is making phone call, the electron EDA signal, HRV signal, and interaction sequence and other prediction model combining all together provides really high accuracy. So from our experience, we have seen that 100% acceptance of wiring waistband and 71% of acceptance for signing consent on using cameras, and 0% failure rate of collecting continuous data using our smart home. Thank you so much for listening to my talk. Take care.
Welcome to my presentation. I'm Florian Diemer, and today I'm going to talk about TinnituSense, which is a smartphone app we created in order to perform mobile electroencephalography on standard Android smartphones. The application allows acquiring the EEG data in real time from an EEG amplifier and visualizes the acquired data on the graphical user interface. During this presentation, I'm first going to talk about tinnitus and mobile health. Then I'm going to introduce the TinnituSense app. This includes the architecture and also the supported features. After that, I'm going to talk about EEG data acquisition, including the parser model as well as the data flow. Subsequently, I'm going to talk about the evaluation by first introducing the experimental setup and then talking about the results and the contributions. This is concluded by a summary and a recap. Tinnitus is a complex and heterogeneous disorder associated with causing the perception of a continuous clicking, ringing, or buzzing sound in the ears in absence of any external sound source. Approximately 15% of the world's population suffer from tinnitus, out of which 2% experience a substantial decrease in quality of life. People who perceive tinnitus have defined its properties to be like singleton, multiton, noise-like, or having no tonal quality at all. It can be constant, pulsating, or intermittent, and can occur instantaneously or progress over time. In addition to general health complications, some evidence suggests that tinnitus might also be responsible for provoking and getting influenced by other psychological disorders like fatigue, stress, anxiety, depression, amnesia, or insomnia. It is also established that tinnitus affects the common as well as the social lifestyles of its sufferers. Since tinnitus has that many characteristics, it is important to collect as much data as possible to allow a proper therapy selection for each individual patient. Among a variety of smartphone-based solutions for tinnitus management, smart mobile crowdsensing can be a viable solution in understanding tinnitus. Smart mobile crowdsensing mainly comes in two flavors. First, the participatory sensing, where the user voluntarily participates in contributing information, like filling out questionnaires or something like that. And second, opportunistic sensing, where the data is sensed, collected, and shared automatically without user intervention. This can be achieved either via using the embedded sensors of smartphones or by coupling external auxiliary sensor devices, like for example an EEG device. Smart mobile sensing can be applied on different levels, like individual sensing to monitor movement and activity, group sensing to measure quality of air or sound pollution, and urban scale to track spread of a disease, like for example the current COVID pandemic. Smart mobile crowd sensing solutions can be applied with specific focus on people or environment. Both is also possible. Nevertheless, smartphone apps are also interesting, as smartphones provide an application ecosystem which is extendable to program and include new apps targeting different health problems at almost no cost. This is also the case with tinnitus. Herein, to better understand the phantom phenomenon of tinnitus, smartphone-based ecological momentary assessments, short EMA methods, can be utilized to capture the variations in tinnitus perception and link them to current surrounding or environmental conditions, as well as with the electroencephalographic conditions of the patient. Individual tinnitus profiles, along with existing standard tinnitus questionnaires like Tinnitus Handicap Inventory, Tinnitus Functional Index, and mini tinnitus questionnaires, can be beneficial for tinnitus-related assessment. For environmental monitoring, the embedded sensors of the smartphone, like the motion sensors, environmental sensors, and position sensors, can be employed. For EEG or electroencephalographic data, mobile and ambulatory EEG data systems can be highly beneficial. So let's have a look at the technical architecture of the TinnituSense app. The application is implemented in Java and runs on standard Android devices. The application consists of several modules, which I'm going to introduce briefly. There's a tinnitus profile, as you can see here. The tinnitus profile includes general information about the patient's tinnitus state. We also support to fill in some questionnaires, This includes the THI, the TFI, and also the mini TQ. The sensor services allow environmental monitoring by using the smartphone embedded sensors, like for example the light sensor, the pressure sensor, or the temperature sensor. The acquired sensor data is directly visualized on a graphical user interface. This allows the user to check the collected data. Besides using the embedded sensors of the smartphone, it is also possible with the TinnituSense app to directly communicate with an EEG amplifier. For starting an EEG recording session, the patient has to wear an EEG cap which is connected to the EEG amplifier. The EEG amplifier directly sends the acquired data to the Bluetooth connection manager, which provides the data to the EEG data receiver. The implementation of the EEG data receiver was the main topic of our paper, and therefore I'm giving you more information on the following slides. For now, it's enough to know that the component consists of two submodules, which are the EEG data parser and the adapters. The EEG data parser is responsible for transforming between the EEG amplifier device-specific data format and the native Android data structures. The adapters are a controller between the parser, the data model, and the visualization component. After processing the incoming data, the data is forwarded to the EEG visualization component, which visualizes all the data on the graphical user interface similar to the embedded sensors. The visualization component also makes sure that only the EEG channels which are currently visible on the graphical user interface are updated in order to save energy. On this slide, a screenshot of the application's home screen is shown. Each component we discussed on the previous slide has a separate button on the home screen. This allows quickly accessing the components. By clicking on the Sensors button, the embedded smartphone sensors can be accessed, which allows enabling or disabling individual sensors. By clicking on the Survey button, a survey can be filled in, and the user profile can be accessed by clicking on this button. The External Sensors button allows to connect to an external EEG amplifier. Currently we support the Brain Products LiveAmp16. After establishing a connection to the EEG amplifier, a workspace can be specified, and then the EEG recording session can be started. The TinnituSense application uses workspaces for managing the EEG configuration. This allows reusing a configuration for subsequent runs, or to adjust single values by keeping the remaining configuration the same. A workspace includes information like name, recording mode, and sampling rate, and also the enabled EEG channels can be specified. After creating a workspace, it shows up in a list, which makes it possible to edit a workspace. Once the configuration is done, a workspace can be selected by clicking on its name. This will result in showing up the visualization screen, as you can see on this screenshot. For EEG data acquisition, there exist multiple options. The data can be recorded and visualized at the same time. The data can be only monitored, which means it's only visualized. And it's also possible to start and stop a test signal, which you can also see on this screenshot. On the last screenshot, you can see a EEG sample signal. The screenshots already show the final results after implementing the EEG data receiver component. Relating to the screenshots, this includes configuring the EEG amplifier by sending a workspace, starting or stopping an EEG data acquisition session, and extracting the actual EEG channel values from the received EEG data packets. Each of those operations corresponds to one of the available packets of the parser model, which will be discussed on the following slide. As abstraction from the actual byte representation, we use packets for the parser model to allow simple data access. Packets are composed of a header and a data section. The header contains general packet information like packet size and type, which you also can see here. The actual content is stored in the data section. There exist three main types of packets, which are marked in blue in the parser model. Request packets are used for sending information to the EEG amplifier, like a workspace, or to request information from the device, for example the current EEG amplifier status. Hence, request packets are always sent from the smartphone to the EEG amplifier. The getByte representation method allows retrieving the packet's actual byte representation. This can be used to send the data to the EEG amplifier. In contrast, the other two main packet types, which are the response packet and the data packet, are sent from the EEG amplifier to the smartphone. Therefore, those packets are grouped to a device packet. The getPacketRepresentation method enables parsing the received byte representation to the respective packet representation. Response packets usually contain the response to previous request packets, like the current EEG amplifier status, or simply acknowledge a request packet, like receiving a workspace. In general, each request packet is followed by a response packet. Data packets are used for sending the EEG data from the EEG amplifier to the smartphone. Compared to response packets, data packets are usually sent continuously after starting an EEG data session until the session is stopped again. The three main packet classes are all abstract Java classes, which means that no instance of them can be created. Instead, those classes are used as base classes for implementing the concrete packet types. For example, there exists a device status response packet, a command acknowledge response packet, and an acquisition data packet. As data model, we use plain old Java objects, which allow simple data exchange between the EEG data receiver and the Android app. For example, an object for storing device information or acquisition data exists, as shown in the top right corner. Please note that our implementation specifically targets the Brain Product's LiveAmp16 EEG amplifier. However, we designed the parser model flexible by providing an abstraction from the actual byte representation. This allows to keep the model for different EEG devices, since most EEG devices offer similar operations, and only replace the byte representation by providing alternative implementations for the getByteRepresentation and getPacketRepresentation methods. The adapters component is a controller that mediates between the EEG data amplifier, the data model, and the Android app, as already mentioned. The adapters component consists of the output adapter and the input adapter subcomponents. The output adapter provides simple access to all important send operations, like sending the recording configuration or starting and respectively stopping an EEG data acquisition. The input adapter provides a handle method, which takes the received bytes as parameter and uses the parser component to transform the byte representation to the packet representation. Let's have a look at a short example using the general data flow as shown on this slide. A user wants to request the current EEG amplifier status by interacting with the graphical user interface. This initiates an EEG device interaction operation. In this case, the output adapter's getDeviceInformation method is invoked, and internally, the respective request packet is built. Before sending the data via Bluetooth to the EEG amplifier, the request packet's getByteRepresentation method is used to retrieve the actual byte representation. Subsequently, the EEG amplifier processes the request and sends a response packet, which is in this case a device status response packet, including the current device status. After reading the bytes, they are forwarded to the input adapter's handle method. Internally, the parser component is used to determine the packet type and to parse the included data to the respective packet representation. Finally, the response is displayed on the graphical user interface by accessing the packet data using the simple data structures as defined in the data model. To objectively evaluate the developed app, 3 different observational parameters were defined. The latency parameter provides insights into the improvements made in the TinnituSense app by directly acquiring the EEG data on the smartphone from the amplifier device using the Bluetooth connection. The current paradigm of acquiring EEG data on the smartphone is limited. Usually the EEG data is acquired on the smartphone either through a cloud service or through remote data access. In both these situations, the EEG data acquisition on the smartphone involves requiring additional hardware. This not only limits the mobility, but also includes additional delays. The performance and battery parameters will provide insights into the capability of current smartphones to acquire real-time EEG data. The developed app was evaluated on 4 different smartphones with different hardware configurations and Android versions, as shown in the table. The Android Studio profiler was used to record the evaluation data. 5 different runs with continuous EEG data sampling at 250 Hz were performed and the data was collected. The table shows the latency results of acquiring EEG data directly on the smartphone. Please note that the total latency to prepare and send a request to the amplifier, as well as to receive and parse a response from the amplifier, is 26 milliseconds. This is a significant improvement as opposed to using a remote data access where the average delay times are in the range of 50 to 100 milliseconds. For the performance results, we can see that all smartphones were capable of acquiring EEG data with limited resource consumption except the LG G6 phone. This can be attributed to the fact that it only has 4 CPU cores. This table presents the results of the overall battery runtime of the 4 smartphones for continuous sampling EEG data. From the table we can see that it is possible to run EEG data acquisition for a long time. As most EEG data acquisition sessions only last for 40 minutes, this should be sufficient. The proposed approach contributed by helping with the collection of brain imaging data in real-world settings or places where laboratory EEG setup is not practical, without the need of an added hardware, and in a cost-efficient fashion using the pervasive smartphone devices. The approach will also allow researchers to monitor brain activity of tinnitus patients in a real-world environment without limiting the mobility, specifically since smartphones are literally mobile devices. The proposed app will also enable correlation of tinnitus-related data with weather data, as well as with brain imaging data for large-scale studies. For instance, to collect evidence for new facts regarding tinnitus with the help of ambulatory brain imaging data. And the proposed app will serve as a significant asset for brain imaging and neuroimaging research, not only in the context of tinnitus, but the approach is generic enough to be applied in other domains. Here is a short summary of what I talked about today. I started with a brief introduction of tinnitus, mobile crowdsensing, and ecological momentary assessment. Then I introduced the TinnituSense app architecture and also the supported features. Afterwards, I talked about the EEG data acquisition. This included the parser model as well as the data flow. This was concluded by a short example which showed the interactions between the smartphone app and the EEG amplifier. Finally, I talked about the evaluation results regarding the latency, the performance, and also the battery consumption. Please note that this work was supported by the European School of Interdisciplinary Tinnitus Research. For additional information about the project, please visit their website. Thank you very much for attending the presentation. Hopefully it was an interesting experience for all of you. If you have any questions, please feel free to ask them.
Hello everyone, welcome to my presentation. Today I'm going to present our paper, MobDL, a framework for profiling deep learning models, a case study using digital health application. I'm Abdurrahim Mohammad Furkan from Swinburne University of Technology, Australia, and I'm presenting on behalf of my all co-authors. So here is a quick overview of our paper. We presented a framework called MobDL, which is used for profiling and evaluating deep learning models. These deep learning models mostly run on a smart mobile device. We proposed a novel evaluation methodology for conducting quantitative comparison of various deep learning models that runs on mobile devices. And our key focus area is the digital health. We have used 3 diverse digital health applications around medical imaging and sensor data. We also conducted an extensive experimental evaluation using several deep learning models. So here are key motivation of our paper. We know nowadays smart mobile device that coupled with artificial intelligence technique has been emerged so fast that it's becoming a key enabler of modern digital health application. deep learning models is gaining significant momentum for onboarding analysis of data using AI approaches. But not much progress has been made at present because there is a lack of proper framework for profiling. We know that deep learning models are extensively used in digital health applications, such as we can see, many medical imaging applications or sensory data analysis. So, some key challenges we face that digital health applications are increasing, but there is a high demand that it's going to be in mobile, because the healthcare professional require instant decision-making capability, and sometimes they would prefer to work in remote offline environments, so you don't have internet to always connect, talk to the cloud and run extensive AI techniques in the cloud to get the result. And there is a concern because this is a digital health or health data. There is an issue around data privacy. So there is increasing need to understand the performance of deep learning model on mobile devices. Based on this, we have this key contribution for our paper. So we proposed a systematic architecture for evaluating different deep learning models, in particular convolutional neural network or CNN on mobile device. We established a common performance matrix that we are going to use to profile CNN models. And we conducted a comprehensive experimental evaluation for validating the effectiveness of our proposed framework using diverse datasets such as from medical images and biomedical signals. So here is an overall architecture of MobDL framework. Our input data source can be from diverse sources such as a person wearing wearable sensor. It can be a sensor data stream, a person who is in a smart home environment, and IoT sensor connected to the smart home can generate signals from IoT devices, or the data can come from different medical imaging devices such as microscope or MRI scan. So these image data generates from medical devices, and all those input data sources are stored in a cloud server because deep learning model training is extensive. So we prefer to store them in cloud and run different deep learning models for generating the estimated outcome for the model. So once we have the trained model, we can use them classification. So here we can run the classifier in the mobile device to produce the evaluation matrix, or in the cloud as well to produce the same evaluation matrix. So our evaluation framework contains those evaluation metrics, and these are different software tools we used for our framework, which I'm going to describe later. And the deep learning models can solve the different application area problem, such as object classification in medical images, or activity recognition, or disease identification. So some components of our MobDL framework are the first is the deep learning models. As we have seen in this architecture, we are running different deep learning models. So we mostly use pre-trained CNN. They are ResNet, such as ResNet, VGG, MobileNet, or CNN LSTM. And another key component of our framework is the evaluation framework, which comprise of 11 evaluation metrics. They are model size, accuracy, precision, recall, F1 score, mean average precision, model loading time, recognition time, round trip time, CPU usage, and memory. As we know, the model size, because different deep learning model has different size, so we need to understand which one is large or which one is small in size, and these are mostly machine learning or deep learning performance measure. And to understand the performance of mobile, CPU usage, memories, these metrics are mostly used. Here are some key software tools we used in the implementation, such as Keras, TensorFlow Lite. So TensorFlow Lite is a mobile version of a TensorFlow, and Keras is one of the popular framework for CNN model construction and running, OpenCV for image processing, and Android SDK for running our generated application on a mobile device. For the dataset, we have used three types of datasets. So first one is the new cell image dataset. These are medical image and generated from microscope. So this sort of image help to understand the underlying biological process in human health. Different deep learning models used to identify the cell object within the images, and we have used an open source dataset from Kaggle. The second one is the malaria parasite dataset. This one also are microscopic images, and they are taken from human blood samples, and they contains different type of infected cells due to malaria, like these are 5 names. And CNN models are used to identify those unaffected cells and distinguish between affected and different unaffected cells. Here we also used publicly available data. Another dataset is for human activity recognition, which is a wearable sensor data stream taken from waist-mounted sensor and used for 6 activities classifications, such as walking, walking upstairs, walking downstairs, sitting, standing, and lying. This is also a publicly available dataset, and we have used CNN LSTM for the classification of such dataset. These are our experimental setup for evaluation. So as we described, for the data set, we have used image data and sensor data as a time series. For health data, we used MAX RCNN as deep learning method and 3 backbone network. They're ResNet, MobileNet, and InceptionNet. And where we evaluated the model and which sort of software library we used. For the mobile device, we have used Samsung Galaxy Tab 3 and Samsung Note for evaluation. And we follow 2 approach. In the first approach, the model is loaded in the main memory at the first, and for prediction was performed for each of the images. And the second approach, every time we run a prediction, the model was loaded every time to understand the difference. As we already mentioned, that we have used 4 deep learning models, which are ResNet, MobileNet, and InceptionNet, and CNN LSTM. So CNN LSTM is only used for the sensory stream, and each of them is picked due for certain purpose. Like a ResNet is a high performing CNN. MobileNet, it is a CNN based suites for a mobile device, and InceptionNet is a representative of a lightweight CNN. Here are some snapshot of evaluation outcome using mobile device. So first one is the new cell detection. As you can see, after running deep learning model, the model is capable of detecting the new cell in the images, and it reports the recognition probability. In the malaria parasite, this is also snapshot for Samsung Galaxy S3, and it detects different unaffected cells in the malaria parasite image and highlighted them. In human activity recognition, it recognizes human activity such as sitting, and it also reports about probability. So our implementation app is publicly available, and this is the GitHub link. Anyone, you can go and download and use our profiling framework. So here is overall result of our evaluation framework. For each of the data set, we presented the evaluation metrics results that produced by different deep learning models, and 3 data set. Like for Newseli and malaria, the main focus of the performance measure was mean average precision, and the outcome for like model loading time, round trip time, CPU memory, etc. are mentioned. And then the human activity recognition, all the results are here. So here is another snapshot. If we compare two devices, one is high performing Samsung Galaxy Note 10 Plus and one is Tab 3. As we can see that CPU usage, mobile in terms of memory or modern loading time, everything is higher in Tab 3. The key observation from the tables that we presented earlier 2 slides back is that some of the CNN models that run on mobile device such as suitable for mobile device such as mobile net perform the recognition faster, like 23.08% faster than a bigger network such as ResNet 101. However, ResNet has the highest accuracy, so if we use mobile net, you need to compromise 10.62% less accuracy. Bigger CNN models such as ResNet 101 exhibit higher performance, but this is the worst in terms of model loading time because the size is larger. The shallow CNN networks such as InceptionNet use less memory but requires higher CPU utilization, but accuracy is still lower than bigger networks such as ResNet 101. For sensor data or time series data, the lightweight deep learning models such as CNN LSTM can perform the recognition task very quickly with good performance. So here is the summary of our paper. We presented a novel framework for evaluating and profiling deep learning models on mobile devices. Our framework contains 11 metrics for evaluating CNN models in mobile as well as cloud context. Our focus was in two specific digital health data modalities. One is microscopic captured images such as cellular data, and another one is IoT wearable sensor record physiological signals. Our result demonstrated the usefulness of the proposed framework, and this one is a comprehensive and quantitative profiling tool for evaluating and selecting deep learning models that are fit for the purpose in the mobile context. Thank you very much.